Hello there, and welcome to Life Beyond Scene, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're drifting northward toward a place that looks calm on a map, reasonable in a textbook, and almost friendly in a summer postcard. But maps can be polite to the point of dishonesty, and postcards have a habit of leaving out the hard parts. Because the waters we're talking about tonight, the Great Lakes, are not always gentle, and they are certainly not always safe. In fact, when November settles in and the air sharpens and the weather loses its patience, these inland seas can become some of the most dangerous waters on Earth. That is the quiet mystery we are settling into tonight. Why do the Great Lakes turn deadly when autumn gives way to winter? Why does November, in particular, hold such a grim reputation among sailors, fishermen, freighter crews, and anyone who has spent enough time near these waters to know that they do not care much for human confidence? It is a question with weather in it, certainly. There is cold air, warm water, fierce winds, and waves that build with a kind of relentless logic. There is geography in it too, and history, and maybe a small lesson about what happens when a body of water is large enough to behave like an ocean, but familiar enough that people sometimes forget it can. There is also something a little unsettling about the phrase Great Lakes itself, isn't there? It sounds so manageable. It sounds like a pleasant school subject, or a weekend drive, or perhaps a very ambitious holiday brochure. Great Lakes, lovely name, solid, upright, trustworthy. It does not sound like the sort of place that would hurl steel ships into chaos, erase horizons in freezing spray, or make seasoned captains measure the sky with the seriousness usually reserved for surgeons and bomb disposal experts. And yet every year, especially as November arrives with its usual collection of bad intentions, the lakes remind everyone within reach that size matters, cold matters, wind matters, and fresh water can be every bit as unforgiving as salt. Before we get into all of that, I would love to know where you are listening from tonight and what the weather is doing just beyond your window. Is it still and quiet where you are? A soft kind of evening maybe? Or has the wind already turned up and started pushing at the glass with that familiar restless hand? Perhaps you are listening from somewhere far from any large body of water at all, somewhere landlocked and dry, and the very idea of a lake becoming monstrous feels faintly unreasonable. Or perhaps you know exactly the kind of weather I mean. The sky lowering itself all afternoon, the air taking on that metallic edge, the trees moving differently, the sense, before anything dramatic has even happened, that the world has made up its mind about something. If you find this journey soothing, interesting, or simply a good way to wind down at the end of the day, I would be ever so grateful if you gave the video a like, maybe subscribed, and stayed with me for a while longer. It helps this quiet corner of science and story find the people who need it, especially the ones looking for something calm to listen to while the rest of the world insists on being loud. And if tonight's subject sounds a little stormier than usual, do not worry. We're not here to be tossed overboard. We're only here to watch from a safe distance, ask sensible questions, and admire the kind of power that does not care whether we have understood it yet. Now, when most people hear the word lake, they think of something bounded and knowable, a place for skipping stones, renting kayaks, losing one's sandal on a muddy shore, and pretending for 30 whole minutes that you're the kind of person who enjoys getting up before sunrise. A lake is supposed to sit there. A lake is supposed to stay within its lane. A lake is not, generally speaking, expected to generate waves high enough to make a freighter vanish into troughs of dark water, nor should it be expected to produce storms with names that linger in local memory for decades. And yet the Great Lakes do all of this, not because they are strange exceptions to nature, but because they are enormous, exposed, and caught in a region where autumn can become unstable in a hurry. That last part matters. November is not just another page on the calendar. Around the Great Lakes, it is a season of collision. Summer's leftover warmth clings to the water longer than the land can manage. Cold air begins sweeping down from the north and west with increasing boldness. storm systems strengthen, pressure gradients tighten, winds gather themselves and move with purpose. The lakes, still carrying a memory of warmer months, offer up moisture and heat into a colder atmosphere that is more than happy to make trouble with both. And once the wind begins to push across a long enough stretch of open water, the surface responds the only way it can. It rises, it builds, it turns muscle into motion. The result is not merely bad weather, it is a whole machine of danger, assembled out of ordinary ingredients: air, water, temperature, distance, timing. Nothing supernatural, nothing dramatic for the sake of drama, just physics doing what physics does when given enough room and enough contrast. That, I think, is part of what makes these storms so compelling. A thunderstorm over a city feels like an event. A gale over the Great Lakes feels like a system. It has scale. It has structure. It has a kind of impersonality that can be more unnerving than anger. The water is not furious with you. The wind does not dislike you. The storm is not making a point. It is simply unfolding, and if you happen to be in the way, that is your problem rather than its own. People who live near these lakes have known this for generations. Long before satellite loops and marine forecasts and radar imagery in neat glowing colours, there were stories, habits, warnings, and local rules passed down in practical language. Watch the sky. Respect the season. Do not assume calm water means safe water. If the wind shifts and the temperature drops, pay attention. If someone older than you says not to go out, try not to make that your moment of rebellion. The lakes educate people in very plain terms. Some learn by watching from shore. Some learn from a vessel rolling under a sky that no longer looks familiar. Some, sadly, do not get the chance to pass the lesson on. And that is where tonight's subject begins to deepen. Because this is not only a story about weather, it is also a story about human expectation. We are very good at underestimating things that look familiar. We do it with roads we drive every day, tools we use too casually, and bodies of water whose names we learned early enough to think we understand them. Ocean. Now there is a word that makes people cautious. Ocean gets respect. Ocean has branding. Nobody looks at the Atlantic and says, well, it's probably fine, but lakes, especially in the imagination of people far away from them, can seem modest by comparison, contained, limited, tidy. The Great Lakes are none of those things. They hold vast volumes of water, create their own local weather, stretch to horizons, and in rough conditions can deliver the same kind of punishment many people associate only with the sea. In a way, the term inland sea is much closer to the truth, though even that can be misleading if it sounds too elegant. Because this is not just about grand scenery and distant freighters moving like small buildings through the mist. It is about the mechanics of danger. It is about how wind over fetch, that long uninterrupted distance across open water, allows waves to grow larger and steeper. It is about how cold water shortens survival time if someone goes overboard. It is about how late-season storms can intensify quickly, and how freezing spray can add dangerous weight to a vessel. It is about how November sits at a crossroads, where the lakes are still energetic from warmer months, but the atmosphere has become far more aggressive. Even saying it plainly, it still sounds a little unfair. Water above, water below, and the air itself deciding to become a problem in between. You can feel the ingredients of this story even on land. Anyone who has stood near a Great Lake in late autumn knows that the mood can change with startling speed. A beach that seemed open and bright in the afternoon can become a place of stinging wind and heavy surf by evening. The sound changes first sometimes, then the light, then the colour of the water, which can shift from blue or grey into something harder, flatter, more metallic, as if the lake has stopped pretending to be recreational. Seagulls lower their flight, trees lean, small craft warnings start sounding less like suggestions and more like pleas from people who have seen this before. And still, people go out. Of course they do. Commerce moves on schedules, Fishing seasons do not always align with comfort. Ferries, workboats, tugs and freighters exist because someone has to cross, haul, deliver, tow, or earn a living. Even recreational boaters can find themselves making optimistic choices, which is a very refined way of saying, well, it looked okay when we left. Human beings are excellent at mistaking temporary luck for sound judgment. The lakes, particularly in November, are equally excellent at correcting that mistake, not cruelly, efficiently. There is another reason this subject holds on to the imagination, and that is the combination of familiarity and scale. The Great Lakes sit beside cities, towns, lighthouses, highways, cottages, forests, steel mills, marinas, and neighbourhoods. They are woven into ordinary life. Children grow up near them. Families picnic beside them. People jog along their edges, commute across bridges near them, build economies around them, and watch sunsets over them with the casual confidence of those who think the scenery is mostly on their side. Then November comes, and the same water that reflected sailboats and summer clouds begins producing walls of spray, monstrous rollers, and a kind of cold hostility that makes all casual language feel slightly ridiculous. There is something deeply humbling in that change, not because nature has become evil, but because it has reminded you that friendliness was never part of the contract. That may be the main thread we keep returning to as we move further into this story. The lakes turn deadly, not because they transform into something else, but because certain conditions reveal what they have always been capable of. November does not invent their power. It uncovers it. It aligns the atmosphere and the water in ways that allow the full size of the system to express itself. A calm August shoreline can hide the same depth, distance, and force that a November gale will expose. The difference is not identity. The difference is arrangement, same lakes, different terms of engagement. Once you start looking at it that way, the whole region changes character. The map becomes more serious. Lake Superior stops being merely the largest and starts feeling like a place where weather has enough room to become organised and mean about it. Lake Michigan, Lake Huron, Lake Erie, Lake Ontario, all distinct, all connected in ways both physical and historical, become parts of a wider freshwater world whose dangers are not always obvious from shore. Shipping routes turn into threads of risk. Harbours become thresholds between shelter and exposure. Lighthouses begin to look less decorative and more like blunt admissions that this place has required warning systems for a very long time. And then there is the human memory of it all, which gathers around certain storms, certain dates, certain vanished ships, and certain names spoken with a quiet change in tone. Ask around the lakes, and November is rarely discussed as a neutral month by those who know the water well. It carries stories, not in a mythical sense, not in a campfire exaggeration sense, but in a practical regional memory built from weather records, wrecks, rescues, and narrow escapes. Some of those stories are famous far beyond the lakes themselves. Some live only in families, ports, Coast Guard stations, and local newspapers that once printed grim details beside advertisements for winter boots and kitchen ranges. Together they form a kind of archive of respect. You can ignore it, of course, people always can, but the lakes do not care whether you have read the archive before arriving. I think that is why this subject suits a quiet evening so well. It is dramatic, certainly, but not in the loud or theatrical sense. It is dramatic the way real things tend to be, gradual, physical, inevitable once the conditions line up. There is no villain to argue with, no twist that appears from nowhere. There is simply a pattern that becomes visible if you sit with it long enough. The lakes are vast. November is unstable. Warmth lingers in the water. Cold arrives in the air. Wind builds over distance. Waves answer. Ships move anyway. And somewhere in that sequence lies the reason so many people around these inland seas speak of this season with a kind of earned caution. So as we continue, we are going to take our time with that sequence. we're going to look closely at what the Great Lakes really are, because understanding their scale is the first step in understanding their danger. We're going to see why November is different from the months around it, why the weather sharpens, why the water keeps contributing energy, and why storms here can become far more severe than someone unfamiliar with the region might expect. We will move gradually, as always, not rushing past the useful details. Because the interesting thing about dangerous places is that they often become less mysterious the more carefully you look at them. Not less powerful, certainly, just easier to respect for the right reasons. For now, though, it is enough to sit at the edge of the question and let the scene settle into place. A cold month, a broad reach of dark water, wind with miles to work on the surface, harbours tightening into evening, crew members checking forecasts twice, shorelines emptying out. Somewhere overhead, another pressure system organising itself with complete indifference to plans, cargo schedules, and human optimism. The lakes do not need to announce what they are about to do. They simply begin, and if you know how to read them, you can tell when the tone has changed. What looks from a distance like weather moving through is, up close, a complicated conversation between heat, cold, air, water, and time of year. And that is where we should linger next, because before a place can turn deadly, it must first be understood properly. The Great Lakes are often introduced as if they are oversized versions of ordinary lakes, but that is much too simple for what they actually are, and the scale of them changes everything that follows. It helps, I think, to begin by correcting a very common misunderstanding. When most people hear the word lake, they picture something comfortably bounded. A place with a visible opposite shore, a few fishing boats, perhaps a dock with one suspiciously loose plank, and a child somewhere dropping a sandwich into the water by accident. A lake, in the ordinary sense, feels local. It belongs to a town or a park or a summer memory. The Great Lakes do not behave like that. They stretch across the United States and Canada, run more than 750 miles from west to east, and form one of the largest surface freshwater ecosystems on Earth. They hold about 84% of North America's surface freshwater and roughly 21% of the world's surface freshwater. Even before you get into storm ships or November, that scale alone should make a person sit up a little straighter. And scale is really the first thing that changes the conversation. Taken together, the 5 lakes cover about 94,250 square miles of water. That is not a charming local reservoir with aspirations. That is a freshwater expanse so broad that the horizon behaves the way it does at sea. Their combined volume is more than 22,000 cubic kilometres, and the shoreline, including islands and connecting channels, runs more than 10,000 miles. You can drive around a modest lake on a lazy afternoon and stop for pie halfway through. You do not casually do that with a system like this, unless you have a very open calendar and a firm commitment to snack planning. These are large basins with large fetch, large weather responses, and large consequences when conditions deteriorate. It is also worth noticing that they are not 5 separate blue puddles placed side by side for convenience. They are connected, and that matters. Water flows from Lake Superior and Lake Michigan into Lake Huron, then through Lake St. Clair into Lake Erie, over Niagara Falls into Lake Ontario, and onward through the St. Lawrence River to the Atlantic. NOAA describes the system as 5 large lakes, 1 small lake, 4 connecting channels, and the St. Lawrence Seaway. So when we talk about the Great Lakes, we're not really talking about isolated bodies of water. We're talking about a freshwater network, a linked inland corridor that behaves like a regional system in both geography and commerce. It is less like a collection of neighbourhood ponds and more like a chain of inland seas that happen to be made of fresh water instead of salt. That phrase, inland seas, is not just a dramatic flourish either. It is one of the few ways to explain them without understating the case. Lake Superior alone is about 350 miles long and reaches a maximum depth of 1,332 feet. Lake Michigan drops to 925 feet. Lake Huron reaches 750. Lake Ontario goes to 802. Even the shallowest of the five, Lake Erie, with a maximum depth of 210 feet, is still large enough to generate very serious weather and wave conditions under the wrong setup. Their average depths are not trivial, their basins are not small, and their water does not respond like a farm pond having a difficult afternoon. When wind acts on a system this large, the result is not a little chop and some annoyed gulls. The result can be organised, heavy wave action over long distances. Lake Superior makes the point especially well because it sounds, on paper, almost unreasonable. It holds so much water that Britannica notes that, if emptied at its present outflow rate and with no new input, it would take 191 years to drain. That is not a statistic so much as a polite warning. It tells you that the Great Lakes operate on a scale that our ordinary lake instincts are not really built for. Superior is not simply bigger than many lakes. It belongs to a different category of experience. You do not stand at its shore in poor weather and think, "Ah, yes, a manageable body of water." You stand there and begin to understand why the people who work these routes use words like sea room, harbour refuge and respect with very little irony. Then there is the matter of motion, because people often assume that if water is fresh and inland, it must also be relatively quiet. Not so. The Great Lakes are considered non-tidal, but that does not mean their water levels sit there obediently like students during an exam. NOAA notes that true lunar and solar tides on the Great Lakes are tiny, generally less than 5 centimetres, and are overwhelmed by bigger changes caused by wind and barometric pressure. Wind and weather can produce seaches, which are oscillating waves that can be several feet high. In other words, these waters may not have ocean-style tides in the dramatic coastal sense, but they absolutely move, shift, rise, and respond to meteorological force in ways that matter very much to anyone on a vessel or near an exposed shore. Fresh water does not become tame simply because it has skipped the salt. That is another reason the Great Lakes are not just lakes in the everyday sense. They are weather-making surfaces. NOAA notes that water levels and conditions here are driven primarily by meteorological effects, and the broader Great Lakes region contains nearly 20% of the world's fresh surface water and more than 9,000 miles of coastline. That much open water alters nearby climate, influences coastal areas, and creates conditions that people living beside ordinary inland lakes would not recognise on the same scale. The lake's moderate temperatures in adjacent regions affect cloud cover and precipitation, and in colder months help fuel lake effect snow. So even when they appear still from a distance, they are not passive scenery. They are part of the atmosphere's working arrangement, quietly influencing what the air does next. You can see this in the way people live around them. More than 30 million people live in the Great Lakes Basin. Major cities, ports, industrial corridors, farms, fisheries, forests and tourist towns all sit within a region shaped by these waters. The basin supports a significant share of Canadian agricultural production and American farm production, and the lakes provide drinking water, transportation, power, recreation, and ecological habitat on a continental scale. That is another clue that we are dealing with something bigger than the usual mental picture attached to the word lake. Ordinary lakes do not anchor an entire cross-border economic and ecological zone of this size. Ordinary lakes do not become central characters in industry, weather, shipping, and regional identity all at once. Shipping, in particular, is where the difference becomes impossible to ignore. The US Army Corps of Engineers describes the Great Lakes Navigation System as a 1,600-mile deep-water navigation network extending from Duluth, Minnesota to Ogdensburg, New York. It includes commercial harbours, recreational harbours, operational locks, breakwaters, jetties, and hundreds of miles of maintained navigation channels. That is not the infrastructure you build for a harmless inland pond with delusions of grandeur. That is the infrastructure you build because huge volumes of cargo move through these waters, because large vessels need reliable routes, and because the lakes are functionally part of a major transportation system extending deep into North America. Once freighters, locks, channels, and harbour engineering enter the conversation, the old mental picture of a quaint little lake starts packing its bags. And the ships themselves tell the story too. Great Lakes freighters are not tiny pleasure craft in sensible knitwear. They are large working vessels built to carry iron, ore, coal, limestone, grain, and other bulk cargo across long reaches of water where weather can turn quickly and violently. The system's commerce moves millions of tons of cargo every year, and NOAA notes that shipping is an economically efficient way of moving raw materials, agricultural products, and finished goods through the region. That means the lakes are used not as decorative scenery, but as an active freshwater highway. Once you see them that way, much else becomes clearer. Weather here matters because there is traffic to endanger. Wave forecasts matter because there are schedules, crews, channels, and cargoes exposed to risk. Harbours matter because sometimes reaching one in time is the entire difference between inconvenience and disaster. There is also the simple, visual fact of the place, which matters more than people sometimes admit. If you stand at the shore of one of the larger lakes, especially Superior, Michigan, or Huron, there are many stretches where you cannot see land on the other side. The horizon does what the horizon does at sea. The weather approaches across open water. The light changes over broad surfaces. Waves build over long fetch. To the eye and to the body, the experience can feel oceanic even though the water is fresh. That matters because human intuition is heavily visual. If a place looks familiar and bounded, we often underestimate it. If it looks large, remote, and ocean-like, we begin to behave more carefully. The Great Lakes can be deceptive because they are famous, populated, and inland, yet in many conditions they present the same psychological and physical realities people associate with the coast. The map says lake. The experience says something much larger. A useful comparison is this. A small lake is often governed mostly by local conditions. A breeze comes up, the surface roughens. Perhaps someone at the marina becomes more philosophical than usual, and that is the end of it. The Great Lakes, by contrast, interact with large-scale weather systems. Pressure changes matter, wind direction matters, air temperature contrasts matter. The sheer distance over which wind can push water matters. Because the lakes are long, wide, and deep, they have time and room to respond. Weather does not just touch them, it works on them. That is why NOAA and other agencies maintain observation stations, water level monitoring, and wave models for the region. You do not need an elaborate forecasting structure for a pond where the main hazard is losing a flip-flop. You build one when a body of water is large enough to produce conditions with serious consequences for navigation and coastal communities. Another detail people sometimes miss is that each lake has its own personality. Superior is deepest and largest by volume. Erie is shallower and can build steep, dangerous waves faster because of that relative shallowness. Michigan and Huron are linked hydrologically at the Straits of Mackinac and are sometimes treated as a single lake in terms of water level. Ontario sits lower in the chain and connects outward through the St. Lawrence. They are part of one system, but they do not all behave the same way under the same weather. Mariners know this. Forecasters know this. Anyone living near them long enough learns it too. The phrase Great Lakes sounds singular and tidy, but the reality is a family of large basins with shared traits and important differences, each capable of becoming hazardous in its own way. There is a human side to this misunderstanding as well. Because the lakes are freshwater and close to cities, they feel familiar. They're woven into daily life. People jog beside them, fish on them, build homes near them, commute past them, and spend summers treating them as companions. Familiarity is comforting, but it can also dull caution. That is one of the quiet themes running beneath this entire story. The Great Lakes are ordinary enough to be loved casually, and extraordinary enough to punish casual thinking. They can host beach days, ferry routes, and evening walks in one season, then produce gale warnings, freezing spray, and shipwreck conditions in another. Nothing about the water's basic identity has changed. What changes is the arrangement of temperature, wind, season, and exposure. The lakes have always had the capacity. They are simply waiting for the right setup to show it. So when we say the Great Lakes are not just lakes, what we really mean is that the usual word fails to carry the weight of the thing. These are inland freshwater seas with enormous area, great depth, long shorelines, connected channels, active ports, major shipping routes, climate influence, and water level behaviour driven more by weather than by lunar tides. They support millions of people, move commerce through a deep water network, and create conditions that require the same respect one would give to marine environments far from land. Once that is clear, the next part of the story starts making more sense. Because if a body of water this large is still holding on to warmth from the milder months, and the atmosphere above it is beginning to swing colder, sharper, and more unstable, then November is not just another turn of the calendar. It is the point where this freshwater system starts behaving in ways that remind everyone nearby exactly what kind of place it has been all along. And this is where the calendar stops being decorative and starts becoming mechanical. November matters on the Great Lakes not because the name itself carries any special power, but because of where it sits in the yearly sequence. By then, the land around the lakes has cooled quickly. The air masses arriving from Canada and the interior of the continent are increasingly cold and dry, and the lakes themselves are still holding on to a great deal of the heat they absorbed over the summer and early autumn. Large, deep bodies of water do that. They warm slowly and they cool slowly. NOAA and other Great Lakes researchers note that this heat storage is one of the defining features of the system, and that much of the lake's evaporation actually happens in the fall, when cooler, drier air starts moving across relatively warmer water. That seasonal lag is the first reason November changes everything. The lakes are not yet winter cold, but the atmosphere is beginning to behave as if winter has already sent in the paperwork. That mismatch between air and water is not a small detail, it is the setup. During summer, warm air over cooler water often stabilises the lower atmosphere. In late autumn, the arrangement flips. Cold air moving over warmer water becomes unstable. The water transfers heat and moisture upward into the atmosphere, and the air above the lake starts to rise more readily. NOAA's explanations of lake effect processes describe exactly this pattern. Cold air crossing unfrozen, relatively warm Great Lakes water picks up heat and moisture, which can then feed clouds, snow, and more vigorous local weather downwind. Even when lake effect snow is not the main story, the underlying physics still matter. November is the time when the water is still open, still energetic, and still capable of feeding the atmosphere, while the air above it has become much more willing to make trouble with whatever heat and moisture it can get. That contrast turns the lakes from large surfaces into active weather partners. A second piece falls into place overhead. Late autumn is also the time of year when the broader storm track across North America becomes more active and in many cases more intense. Temperature contrasts sharpen across the continent. The jet stream strengthens and shifts in ways that support more energetic low-pressure systems. The Great Lakes sit directly in a region where these systems often pass or deepen, dragging strong winds across long reaches of open water. National Weather Service retrospectives on major Great Lakes storms show this pattern repeatedly, with powerful lows organising over the central United States and then tracking east or northeast through the Great Lakes region during November. That is why November has such a reputation in maritime history here. It is not only that the lakes themselves are primed, it is that the atmosphere is also entering a part of the year when it delivers stronger machinery across them. When those two things line up, stored lake heat below and vigorous storm systems above, the results can escalate very quickly. So November becomes a month of overlap. It has the open water of autumn, but it starts receiving the wind and air mass behaviour more typical of winter. That combination is especially important because by November, there is usually little or no substantial ice cover across most of the system. NOAA notes that the northern Great Lakes may begin to see some ice in late November or early December, but widespread seasonal ice has not yet had time to form. That means the surface is still largely exposed to direct wind forcing. Later in winter, shore ice and broader ice cover can dampen wave action and buffer coastlines. In November, that protection is mostly absent. The wind meets open water, and open water responds with very little restraint. So the month is dangerous not only because storms are getting stronger, but because nothing has yet arrived to quiet the surface. It is all available fetch, all exposed energy, all room for waves to grow. That point about fetch is worth lingering over, because it helps explain why a cold, windy day in November does not stay just a cold, windy day. On a body of water, wind needs distance. Give it enough uninterrupted space across the surface and it transfers more and more energy into waves. The Great Lakes provide exactly that. Once sustained strong winds align over a long enough stretch, wave heights can build with alarming speed. NOAA's wave forecasting work for the region exists precisely because these lakes generate complex and sometimes dangerous wave fields, and the National Weather Service has documented late autumn events where cold air surges over the lakes produced very high waves and significant shoreline impacts. On November 1st, 2020 for example, the Weather Service in Grand Rapids described a cold push over Lake Michigan that helped produce waves of roughly 12 to 16 feet, along with strong gusts and lakeshore flooding. That was not some legendary one-off from a century ago. That was a recent reminder that once November lines up the ingredients, the lakes still know exactly what to do with them. There is also a quieter but important change in what the lakes are losing to the air. During the fall, evaporation rises because the air is cooling faster than the water. NOAA and gale note that most evaporation from the Great Lakes happens in the fall, not in summer, because cooler and drier air flowing over warmer water favours much greater heat and moisture transfer. That transfer affects water levels over the season, but it also matters meteorologically. It means the lakes are actively feeding the lower atmosphere during the very months when storm systems are strengthening. Think of it less as the lakes producing every storm themselves, and more as them contributing fuel, moisture and instability to an atmosphere that is already becoming more aggressive. November is therefore not simply windy. It is a month in which the lakes are still giving, and the air is increasingly able to use what it takes. That arrangement creates a much more efficient system for bad weather than people tend to imagine when they hear the harmless-sounding word lake. By that point in the season, the region is also starting to see abrupt cold air outbreaks. The Weather Service and NOAA descriptions of lake effect and late autumn Great Lakes events repeatedly emphasise cold air descending into the region from Canada or the Arctic. Those air masses do not just make the shoreline feel less inviting, they increase the temperature contrast over the lakes, steepen lower atmosphere lapse rates, and help the wind mix down more effectively from aloft. That is one reason late autumn events can feel so suddenly severe. The day begins with one set of assumptions, and by afternoon or evening the wind field has sharpened, the temperature has dropped, the water is throwing spray, and the horizon has become difficult to read. The Armistice Day storm of 1940 is remembered in part because of its intense daytime temperature drop and powerful winds across the Midwest and Great Lakes. November does that sort of thing with unnerving confidence. It makes transitions happen in a way that leaves little room for anyone still operating on yesterday's expectations. The same timing also helps explain why November holds such a strong place in Great Lakes maritime memory. Some of the region's most destructive storms arrived during this late autumn window, when the water was open, the atmosphere unstable and strong low-pressure systems crossing the basin. The White Hurricane of November 1913, documented by the National Weather Service in retrospective analyses, killed more than 250 people, sank at least 12 ships, and damaged or stranded many more. Later major November storms, including the 1940 Armistice Day storm and the November 1998 gale that followed a track similar in broad terms to the 1975 Fitzgerald storm, reinforce the same lesson. November is not a random date on a list of disasters. It is a recurring setup. The region's history remembers it so vividly because the physics of the month keep offering the same dangerous arrangement again and again, even if each individual storm writes its own version of the damage. Another way to put it is that November removes the excuses. Summer squalls can be blamed on passing instability, and deep winter at least advertises itself honestly. November is more deceptive because the lakes are still navigable, still open, still economically active, and often still visually familiar from shore. Harbours are operating, ships are moving. The season has not locked everything down with heavy ice, yet the margins are shrinking, water temperatures are falling, air outbreaks are harder, daylight is shorter, storm systems are stronger, waves have open room to build, the coast has little ice protection. NOAA has noted that the most significant storms and large wave events on the Great Lakes tend to occur during the colder months of late fall through winter, and that shore ice, when it does exist, acts as a buffer against those waves. November gives you the storms before it gives you the buffer. That is a very poor bargain if you happen to be on the water when a forecast starts going from inconvenient to serious. There is a human consequence to all of this as well, and it is not always dramatic in the cinematic sense. Sometimes it is simply that November compresses decision-making. A captain, a fisher, a crew, a harbour master, a recreational boater making one last run before haul-out, all of them are working in a month where conditions can worsen faster and recover more slowly. When winds build over open water in colder air, spray and wave action become much more punishing. Shoreline communities see erosion and overtopping. Piers become dangerous. The Weather Service's November 2020 Lake Michigan event is a good recent example, with high waves causing minor flooding over piers and along the shore. That sort of event is not necessarily a legendary catastrophe, but it shows the underlying rule clearly. By November, ordinary caution often stops being enough. The lakes are no longer simply large, they have become seasonally primed, and the weather arriving over them has become seasonally stronger. This is when the familiar landscape begins requiring marine seriousness, and perhaps that is the real reason the months stand apart. November is when the Great Lakes stop letting people think of them in summer terms. They are still technically the same bodies of water, of course. Superior has not grown extra depth out of spite. Michigan has not developed a private argument with humanity. Erie has not decided to become theatrical for attention. What changes is the arrangement. The lakes are still holding summer heat. The continent around them is cooling fast. The atmosphere is becoming more dynamic. Stronger low-pressure systems are passing through. Cold, dry air is sweeping across open water. Heat and moisture are rising into the air. Waves are building without much ice to interfere. In a sentence, November is when every important switch is thrown at once. And once that happens, the Great Lakes begin to behave less like pleasant freshwater landmarks, and more like the inland seas they have always been. So when people around the region speak of the gales of November with that particular tone, they are not indulging in folklore for its own sake. They are describing a seasonally reliable change in the operating rules of the lakes. Not every November day is violent. Not every passing low becomes a story that lasts 100 years. But the month marks the point where the system is fully set for danger, in a way earlier autumn often is not. Warmth below, cold above, stronger storms moving through, open water waiting to answer the wind. Once you understand that, the phrase begins to sound less romantic and more like a practical summary from generations of observation. November changes everything because it changes the relationship between lake and air, and once that relationship turns sharp, the surface of the water starts showing the consequences in the most direct language it knows. From there, it is only a short step to the next part of the story, because when these conditions align, and the atmosphere starts organising itself over the basin, a gale is no longer an abstract weather term, it is the next thing taking shape out on the water. By this point, the weather has already laid out the ingredients. The lakes are still carrying stored heat. The air above them is turning colder and more unstable. Stronger storm systems are beginning to move through the basin. So the next step is not mysterious at all. A gale is born the same way many dangerous weather events are born, through a sequence that begins quietly on a map and ends very loudly on the water. And it helps to start with the plainest possible fact, because the word gale can sound old-fashioned, almost literary, as if it belongs in a sea shanty or a captain's journal written by lantern light. But in marine forecasting, it has a very specific meaning. The National Weather Service defines a gale warning as sustained winds or frequent gusts from 34 to 47 knots, which is about 39 to 54 miles per hour. Above that, the terminology changes again. At 48 knots and higher, mariners move into storm warning territory. So a gale is not just a windy day with dramatic personality. It is a real and measurable threshold of danger. That is useful to keep in mind, because it means a gale is not born at the moment the waves start looking intimidating from shore. It is born earlier, when the atmosphere begins arranging itself in a way that will produce those wind speeds over open water. And that arrangement often starts high above the lakes, in the larger river of air that steers weather across the continent. NOAA explains that jet streams form where warm and cold air masses meet, and that dramatic temperature differences can make them much faster, especially in the colder season. In practical terms, that means late autumn is a favourable time for energetic disturbances aloft, the kind that help organise and intensify low-pressure systems below. Before the first harbour line strains or the first freighter rolls, something aloft has usually already begun to lean on the atmosphere in just the wrong way. One of NOAA's basic cyclone models describes the next step neatly. A wave develops on a front when an upper-level low-pressure system embedded in the jet stream moves over that frontal boundary. That is the seed of a mid-latitude storm, what meteorologists call an extratropical cyclone. It does not begin as a spinning monster dropped onto the map fully formed. It begins as a disturbance along the boundary between air masses. At the surface, that disturbance organises into a low-pressure centre, with a warm front extending generally ahead of it, and a cold front trailing behind or to the south and west. The National Weather Service's explanations of surface lows show the same familiar structure. Warm air in the warm sector, cooler air ahead of the warm front and colder air behind the cold front. In other words, a gale is usually born inside an organised weather system with architecture, not chaos. Even its violence arrives in a pattern. Once that surface low begins to strengthen, the pressure pattern around it starts doing the most important work. Wind exists because air wants to move from areas of higher pressure toward areas of lower pressure. The stronger that pressure difference is over a given distance, the stronger the wind can become. NOAA and NWS training materials state this very plainly. The closer the isobars are packed together on a weather map, the stronger the pressure gradient and the stronger the wind. This is one of those wonderfully unromantic truths that sits underneath very dramatic experiences. When a seasoned captain studies a map and sees tight isobars wrapped around a deepening low, they are not admiring the artwork. They are reading force. They are seeing how hard the atmosphere is about to pull. Now place that tightening pressure gradient over the Great Lakes, and the problem becomes much more serious. NOAA's National Data Buoy Centre notes that wind speeds over water and land are not the same. Water presents a relatively flatter surface, while land is cluttered with trees, buildings, rocks and terrain that slow the wind through friction. Their example shows buoy winds greater than nearby land-based winds for exactly that reason. So when a strong low sweeps into the Great Lakes region, the open water does not politely trim the wind down to something manageable. Quite the opposite. Over the lake, the air has room to move with fewer obstructions, and the surface is ready to receive that energy. That is why people standing inland can have one impression of a storm while the water is experiencing something much more severe. The same system can feel rough on land and outright punishing offshore. The atmosphere, meanwhile, keeps building the scene in stages. Ahead of the main low, a warm front often arrives first. The National Weather Service notes that warm fronts are especially common from fall through spring, when larger temperature differences exist across the United States. Warm air rises up and over cooler air ahead of the front, which can produce broad cloud cover and precipitation. This early phase does not always look especially dramatic. In fact, it can be the sort of weather people underestimate precisely because it seems orderly. A grey sky, steady precipitation, pressure slowly falling, a breeze stiffening. Nothing yet that looks like a historic storm to the casual eye. But this is often the quiet administrative portion of the process, the atmosphere arranging the paperwork before it starts throwing furniture. Then comes the part mariners tend to respect very deeply. As the low draws closer, the pressure gradient tightens further, the wind field strengthens, and the cold front advances. NOAA's educational material notes that cold fronts typically move from northwest to southeast and can bring cold temperatures, torrential rain, and high wind speeds. The NWS describes cold fronts as denser cold air, advancing into warmer air, forcing it upward, often with convergence, rising motion, and sometimes heavy weather along the boundary. Even when thunderstorms are not the main threat, the frontal passage can produce a sudden shift in wind direction, a sharp temperature drop, and a burst of stronger gusts. In plain language, this is the moment when a storm stops asking to be taken seriously and starts insisting. On the lakes, that insistence translates quickly into rougher surface conditions, steeper waves, and rapidly shrinking margins for error. There is another piece that matters very much on the Great Lakes, and that is the path most storms take. Michigan C. Grant notes that most storms in the Great Lakes region move from west to east. It also points out that Lakes Erie, Ontario, and Superior are oriented west to east, meaning many storms travel in roughly the same direction as the long axis of the lake. That matters because wind over water needs fetch, the uninterrupted distance across the surface over which it can blow and build momentum. NOAA's wave guidance says plainly that wave growth depends heavily on wind duration and fetch. So a gale is not just born from strong wind alone. It is born from strong wind with room to work. Give a storm a long west to east run over Superior or Erie, and the wind is no longer merely passing over the lake. It is shaping the lake stroke by stroke, piling more energy into the surface every mile it travels. That is why wave forecasts matter so much in this region. Waves are not decorative side effects. They are the visible form of energy transfer from air to water. NOAA explains that waves are commonly caused by wind blowing across oceans, lakes, and rivers, and its wave materials emphasize that stronger wind, longer wind duration, and longer fetch all produce larger waves. The Great Lakes wave prediction system exists precisely because the geometry of these lakes, the wind fields over them, and the nearshore conditions can create very dangerous sea states. A gale on the lakes therefore develops in two linked steps. First, the atmosphere builds wind, then the water turns that wind into motion, and the second step can lag just enough to trick people. The first strong gusts may arrive before the full wave field has matured, which gives the false impression that conditions are merely rough. A few hours later, the lake may look as though it has developed a private grievance. Once a storm has wind and fetch working together, another hazard begins to appear, one that is less famous than waves, but no less important. Strong, sustained wind can physically shove water toward one end of a lake. Michigan C. Grant explains that when a storm moves over a lake, the wind disturbs the water and pushes it in the same direction the storm is moving. This can raise water levels by several feet at the downwind end in what is called a storm surge. After the storm passes and the pressure and wind stop pushing so hard that piled up water can slosh back the other way as a seiche. Small changes may go unnoticed, but larger ones can change levels by several feet in a short time, damage docks, and move anchored vessels violently. So a gale is not just wind and waves arriving together. It can also include the water body itself tilting under the force of the storm, then rebounding after the main push has gone by. Fresh water, it turns out, can sway like a bathtub if the hand on the rim is large enough. At this stage, the gale has become a full system of consequences. The low pressure has organised the air. The pressure gradient has accelerated the wind. The fronts have shifted temperature, moisture and direction. The open water has amplified the surface response through fetch. The waves have grown. The water level may be rising at one end of the lake and falling at the other. And all of this can happen over a timetable that feels uncomfortably brief if you are the one trying to decide whether to run for shelter, hold course, or abandon the idea that the forecast might somehow be exaggerating. This is one reason official examples from the lakes carry so much weight. The National Weather Service office in Marquette documents a late November 2001 storm in which a strong low-pressure system emerged from the plains, producing winds over 55 miles per hour on Lake Superior and waves over 25 feet on western Lake Superior. That is a useful reminder that the birth of a gale is not theoretical. It has a habit of ending in measurements, and yet the process itself remains surprisingly ordinary in structure. No strange atmospheric loophole is required. A gale on the Great Lakes is usually the product of familiar mid-latitude weather doing exactly what it does best when autumn and early winter sharpen the contrasts. A frontal boundary exists. An upper-level disturbance moves in, a surface low develops or deepens, isobars tighten, wind strengthens, a cold front drives through. The open lake receives the energy. Waves and surges respond. The danger accumulates step by step. That is one of the reasons these storms deserve respect. They do not depend on freakish behaviour. They depend on a repeatable arrangement of known ingredients. The atmosphere is not improvising wildly. It is following a recipe that the region has seen many times before. There is also a human side to the timing of all this. A gale is often born before the average observer feels that the day has fully turned against them. Pressure falls are not theatrical. Tightening isobars are invisible without a chart. A long-fetch wind field can still be in its early stages while the shoreline looks merely unpleasant rather than dangerous. This is why marine forecasts matter so much, and why mariners pay such close attention to watches and warnings. A gale warning is not a poetic suggestion to consider a thicker sweater. It is a notice that the atmosphere is expected to produce a specific range of winds over water, winds known to build dangerous seas and severely complicate vessel handling. When that warning appears over the Great Lakes in November, it means the birth is already underway. The weather map may still look organised and civilised. The water will shortly stop caring about that distinction. And perhaps the most unsettling part is how little of this depends on spectacle. The gale does not require thunder every time. It does not need cinematic darkness at noon, or lightning splitting the sky in heroic angles. Sometimes it arrives under a grey ceiling, with temperatures sliding downward, a wind shift that feels manageable for an hour, and then a steady increase in force until the whole lake surface starts behaving differently. That plainness can make it more dangerous, not less. People are good at respecting obvious extremes. They are not always as good at respecting a process that builds in measured logical steps. The Great Lakes, unfortunately, are excellent classrooms for measured logical steps that end in bad outcomes. So when someone says a gale is born on the lakes, what they really mean is that a chain of atmospheric decisions has clicked into place. The jet stream has helped energise a disturbance. A low has organised along a front. The pressure gradient has tightened. Wind has accelerated over relatively low-friction open water. Fronts have shifted the air masses. Fetch has given the wind distance to build waves. Water has started to pile up and sway. By the time the full force is visible from shore, the essential work has already been done. And once that colder air begins sweeping across the still open, relatively warmer lakes, the story becomes even more interesting, because the storm is no longer simply passing over the water starts feeding back. A gale does not fully become itself until the lake begins answering back. The pressure gradient can tighten, the low can deepen, the front can swing through with all the confidence of a bureaucrat carrying bad news. But the real transformation happens when that colder air arrives over water that is still warmer than the season above it. This is one of the central tricks of the Great Lakes in late autumn and early winter. The lakes keep a memory of summer. Noaaglerl describes that plainly as the lake's heat memory, because large bodies of water retain heat from the warm season far longer than the surrounding land does. By fall, and especially by November, the air has cooled quickly, while the lakes are still holding on to warmth they absorbed over months of longer sunlight and milder weather. That lag is not a side note. It is the engine room. It is the quiet imbalance that allows a storm passing overhead to become something more active once it crosses the water. Land cools in a hurry. Soil, roads, rooftops, forests and fields all respond relatively fast when the season shifts. Water is slower, heavier, and far more stubborn. NOAA research on the Great Lakes notes the large thermal inertia of the lakes, meaning they resist rapid temperature change compared with the surrounding land. That difference creates one of the sharpest contrasts in the region's weather. By late autumn, you can have an atmosphere behaving like winter while the lakes are still acting as reservoirs of leftover heat. Not warm in a beach day sense, of course. No one is floating on an inflatable flamingo in the middle of Lake Superior in late November while humming cheerfully about the seasons. Warm only in a relative sense, which is often the most important sense in meteorology. Relative warmth is enough. If the water is warmer than the air above it, and if that air is dry enough and cold enough, the exchange begins immediately. Heat rises from the lake into the lowest layers of the atmosphere. Moisture rises with it. The air nearest the surface becomes less dense than the colder air above, and then the whole thing begins to lift. That lifting matters because a storm is not just wind-shoving water around. A storm is also structure in the atmosphere, and warm water under cold air helps build that structure from below. The National Weather Service explains lake effect processes in very simple terms. As cold air moves over the unfrozen and relatively warm Great Lakes, warmth and moisture are transferred into the lowest portion of the atmosphere. The warmed air becomes more buoyant than the colder air over it, so it rises. As it rises, it cools, condenses into cloud, and can produce snow or other precipitation depending on the exact setup. The important thing for our purposes is not just the snow, it is the instability. A stable atmosphere tends to resist vertical motion. An unstable one encourages it. November and early winter over the Great Lakes often produce exactly that unstable arrangement, and once the air starts rising more easily, storms have more room to organise, deepen, and become unruly. There is a very practical way meteorologists think about this. The NWS office in Duluth notes that lake effect development becomes favourable when the air around 850 millibars, a standard level aloft, is at least 13 degrees Fahrenheit cooler than the lake surface. That is not some mystical threshold at which the clouds receive a formal invitation to start misbehaving. It is simply a useful rule of thumb for measuring how strong the vertical temperature contrast has become. A big contrast means stronger instability. Stronger instability means the air is more willing to rise. And rising air is one of the great enablers in weather. It helps build clouds, deepen bands, enhance moisture transport, and support the kind of rapid local intensification that makes Great Lakes weather so difficult to treat casually. The atmosphere, once properly encouraged, does not need much further motivation. There is also the matter of evaporation, which becomes surprisingly important at exactly the time of year many people assume the lakes should be settling down. NOAAGLERL says most evaporation from the Great Lakes actually happens in the fall, not in midsummer. That seems backward until you remember the temperature difference. In summer, the air over the lakes is often warm and relatively humid, which does not favour maximum evaporation. In fall, cooler and drier air moves over warmer water, and that contrast greatly increases the transfer of heat and moisture from lake to atmosphere. It is a useful reminder that dramatic weather is often built from differences rather than absolutes. The lakes do not need to be objectively hot. They only need to be warmer than the air sweeping across them. Once that happens, the water starts giving up both heat and moisture at the exact moment the seasonal storm track is becoming stronger. It is almost unfairly efficient. That moisture is not a decorative extra. It is part of the fuel supply. Cold season storms crossing the Great Lakes region do not simply pass over a neutral surface. NOAA research indicates that the lake air temperature gradient and surface wind control the vertical heat flux, and that the Great Lakes can generally strengthen low pressure near the surface, though the exact effect depends on the broader background flow. In plain language, the lakes can help intensify the lower part of a storm system when conditions line up properly. Warmth and moisture from the water body can contribute to local pressure falls, moisture convergence, and a more vigorous response near the lake basin. This does not mean the lakes invent every storm that troubles them. The larger cyclone may already be there, advancing with all its synoptic dignity and paperwork. But the lakes can make it sharper, wetter, and in some setups stronger at lower levels. They are not passive victims of the weather, they are active participants in it. That participation becomes easier because the lakes are still mostly open. NOAA-GLERL notes that the most significant storms and large wave events on the Great Lakes tend to occur from late fall through winter, and that shorebound ice later acts as an important buffer against waves and shoreline damage. In November, that buffer usually is not there yet. The water is exposed. The wind has uninterrupted contact with the surface. The lake can evaporate, release heat, feed the atmosphere, and build waves all at once. Later in the season, once broader ice develops in some regions, parts of the system begin to quiet somewhat. November offers no such courtesy. It gives you cold season dynamics with open water access, which is rather like giving a marching band an empty hallway, and then expressing mild surprise at the noise. The surface wind itself matters twice over. First, it drags across the water and grows waves through fetch. Second, it helps regulate how much heat and moisture the lake can push upward. NOAA's cyclone research over the Great Lakes notes that the lake air temperature gradient and surface wind together control the vertical heat flux. So wind is not only the visible menace that throws spray, heals vessels, and rearranges everyone's plans, it is also part of the exchange mechanism. Stronger wind mixes the lower atmosphere more effectively, sweeps colder air across more of the lake, and helps the lake keep feeding the storm from below. That is one reason some systems seem to grow teeth once they reach the basin. Wind strengthens the waves, but it also sharpens the thermal and moisture conversation between water and sky. The storm above and the lake below begin cooperating in the worst possible way. And then the regional geography steps in. The Great Lakes are large enough that this exchange does not stay tiny or local in every case. Open water stretches for long distances. Wind fields can align with a lake's long axis. Moisture picked up over the lake can focus into bands downwind or feed broader cloud and precipitation structures depending on the setup. NOAA-GLERL's descriptions of lake effect events emphasize how hazardous winter weather often develops when cold Arctic air descends over the relatively warm, unfrozen lakes. The moisture transfer can be extensive enough to create intense, narrow snow bands, and the rough winter conditions over the lakes are severe enough that collecting observations is difficult and dangerous for most research vessels and buoys. That last part is worth pausing on. The weather is not merely interesting to scientists, it is physically harsh enough to limit science itself. When your field measurements become difficult because the lake is busy trying to tear the instruments off their moorings, that is usually a sign that the environment has moved beyond brisk. A person standing on shore can sometimes miss how much is going on because the key processes are invisible. You cannot see heat flux with the naked eye. You cannot glance out of a waterfront cafe and say, "Ah yes, the lake air temperature gradient is getting ambitious." What you can see are the consequences. More cloud, more spray, a horizon turning diffuse, snow bands forming downwind, waves building faster than seems polite, air that feels rawer than it did an hour ago, the surface of the water taking on that hard, worked-over look, as though the whole lake has stopped participating in hospitality. By the time these visible signs are obvious, the exchange has already been underway. The lake has already started surrendering heat and moisture. The colder air has already begun to destabilize. The storm is no longer simply crossing the region. It is being modified by the water beneath it. This is also why November storms on the Great Lakes can feel so disproportionately vicious compared with what an outsider expects from the word lake. The danger is not just wind in isolation, and it is not just cold in isolation. It is the combination of open water, stored seasonal heat, strong temperature contrast, active evaporation, instability, and a broader cold season storm track that is already becoming stronger over North America. The lakes are still warm enough to contribute, the air is cold enough to take what is offered, and the storms are energetic enough to turn that exchange into something organised and dangerous. Meteorology is often introduced as a matter of fronts and pressure systems, which it is. But here it is also a matter of timing. If the same low-pressure system crossed the same basin after deep freeze and heavy ice had already locked much of the surface down, the story would be different. November catches the lakes while they are still open for business. There is something almost mechanical about it once you see the sequence. Summer stores heat in the water. Autumn cools the land and the air faster than the lakes can cool. Cold, dry air begins arriving more often. The temperature contrast increases. Evaporation rises. Heat and moisture move into the atmosphere. Instability grows. Low-pressure systems crossing the region can strengthen near the surface or at least find a more supportive lower environment over the basin. Waves build under the same strong winds that are helping drive heat flux. Snow, spray, cloud, and rough seas all become more likely. None of these pieces are strange on their own. Together, though, they make a very efficient machine for late-season danger. It is the sort of machine nature assembles without ceremony, then leaves running while people on shore try to describe it with words like nasty, ugly, or not tonight. Thank you very much. And perhaps the most unsettling part is that the lakes can keep doing this for quite a while before true winter finally suppresses the exchange. NOAAGLERL notes that December is a kind of priming month for ice, when early Arctic air begins cooling the lakes and starting ice generation in bays and along shorelines. Until that process has advanced far enough, the lake remains an exposed source of heat and moisture. So the dangerous season is not a one-day performance, it is a window. November opens it wide, and early winter often keeps it active. That is why the phrase gales of November has such staying power in the region's memory. It points to a month, yes, but also to a physical arrangement that explains why those storms are so effective at becoming memorable. Once the cold air reaches the warmish open water, the lake stops being merely the place where the storm happens. It becomes part of the storm's design. And once that design is in motion, the next thing to reckon with is the surface itself, because all that exchanged energy does not stay politely in the sky. It comes back down in the form of waves. The danger becomes visible here. Until now, much of the story has been atmospheric. Pressure falls, fronts move through, cold air arrives over water still holding autumn heat. But the part human beings actually see, fear, and remember is the surface itself. This is the point where invisible energy turns into moving water, and moving water begins to look less like weather and more like force. NOAA explains that waves are really a transfer of energy created as wind blows across the surface, and that the size of those waves depends mainly on three things: wind speed, how long the wind blows, and fetch, the distance over water the wind blows in one direction. If one of those ingredients is limited, wave growth is limited too. If all three line up over a very large lake in late autumn, The result is no longer a bit of rough chop and some theatrical spray for the tourists. It is a full surface response, built step by step, until the lake starts behaving like a worked-up inland sea. That matters because a lot of people imagine waves as a kind of decoration placed on top of bad weather, as if the real storm is in the sky, and the water is simply reacting for dramatic effect. It is more accurate to say that once a gale has enough room and enough time, the surface of the lake becomes part of the storm's machinery. The wind keeps feeding energy into the water. The water stores and redistributes that energy as wave motion. Forecast officers on the Great Lakes are careful about how they express this because the numbers can be misleading to anyone unfamiliar with marine language. National Weather Service open lake forecasts state that significant wave height means the average of the highest 1/3 of waves, while occasional wave height refers to the average of the highest 1/10. In other words, when a forecast says 8 feet or 12 feet or 20 feet, that does not mean every wave is the same size. Some are lower, some are meaningfully higher. The unpleasant surprises live in that upper edge, and that upper edge can be quite serious. In the National Weather Service review of the November 1998 Lake Superior storm, lengthy gale force winds and occasional storm force winds likely produce significant wave heights of 20 to 25 feet on the open lake, with rare peak waves potentially 1.5 to 2 times that height. Another NWS Marquette summary notes that a November 2001 storm brought winds over 55 miles per hour on Lake Superior, along with waves over 25 feet on the western part of the lake. These are not exaggerated campfire numbers. They're operational and retrospective weather assessments from the lake itself. They also help explain why Great Lakes mariners speak of the season with such seriousness. Once the lake has enough wind, enough duration, and enough fetch, the forecast stops being an advisory and starts sounding like a structural load test for anything floating in its path. Now, here is where the Great Lakes become especially troublesome. Not all large waves are equally dangerous in the same way. The enclosed nature of the lakes tends to produce waves that are steep and short period, compared with many ocean swells, and that steepness matters tremendously. A re-examination of the 1975 Edmund Fitzgerald storm published in the Bulletin of the American Meteorological Society explains that the enclosed nature of the lakes can produce very steep waves, and that steep short-period waves can be particularly hazardous to large ships, especially when they exceed about 5 meters or 16 feet. The same paper notes that wave height depends primarily on wind speed and fetch, but is also substantially affected by the stability of the air over the lake. In unstable conditions, momentum transfers downward more effectively, helping build larger waves. So when the Great Lakes turn violent, it is not only because the waves are high, it is because they can be high, close together, and mechanically punishing. That is a rough combination for any vessel, because steep waves do not merely lift and lower a ship, they strike it harder, faster, and with less recovery time between impacts. That short spacing is one reason the Great Lakes can feel harsher than people expect from freshwater. On the open ocean, a vessel may encounter long swells generated far away, with more time between crests. On the Great Lakes, many of the worst waves are locally generated by the storm itself and remain comparatively compact and steep. That changes the motion entirely. Instead of a slower rise and fall, vessels can experience a much more abrupt sequence of climbing, slamming, rolling, and burying into the next wall of water before they have quite finished dealing with the last one. The danger is not just discomfort, it is loss of control, structural stress, cargo shift, reduced speed, deck damage, and the simple fact that repeated heavy impacts wear down judgment along with equipment. There is something very exhausting about short-period violence. It gives nobody time to regroup, least of all the human body trying to make sensible decisions in cold spray and poor visibility. The lakes also become more dangerous because the same wind that is building the waves is often changing direction as the storm moves through. Ahead of a strong low, the fetch may line up one way across a long axis of a lake. After frontal passage, the wind can shift and begin rebuilding the wave field from a different direction. The National Weather Service summary of the 1975 Fitzgerald storm describes sustained winds from the northeast, east or southeast, before the low crossed Lake Superior, then a shift to stronger northwest winds after the system passed. That means the lake is not always offering one neat pattern of motion. It may be generating one hazardous sea state, then reshaping itself into another as the storm evolves. For ships trying to maintain heading, shelter behind geography, or time a harbour approach, that shifting pattern can be a problem all by itself. A lake in full storm is not a flat surface with a simple wind arrow over it. It is a moving field of forces, and those forces do not always stay politely arranged. Near shore, the problem changes shape again. NOAA explains that as waves approach shallow water, the lower portion of the wave begins interacting with the bottom. Friction slows the base of the wave, compresses its form, and forces the crest higher until it becomes unstable and breaks. NOAA's coastal currents material says much the same thing. As wind-driven waves reach shallower areas, they become steeper, and when they become too steep and unstable, they break. This is why a storm that already looks unpleasant offshore becomes actively violent along beaches, breakwalls, and harbour mouth. The wave is not just arriving, it is being transformed. Energy that was spread through a moving water column is being forced upward and forward into breaking surf. The lake does not become calmer when it nears land. In many places it becomes more abrupt, more vertical, and more destructive. That same transformation is what makes shoreline viewing so much more dangerous than it looks from a comfortable distance. The National Weather Service warns that dangerous currents and breaking waves are common in the Great Lakes region. It notes that even small waves can hit with the force of a car, and that once white water is present, waves are at least about 3 feet, and dangerous currents may also be present. The NWS Great Lakes Safety page also explains that short-period wind waves come in rapid succession, often every 3 to 4 seconds in summer, and that 80% of recorded incidents occur with waves of 3 to 6 feet. That is worth dwelling on because it breaks a very common illusion. People assume the truly dangerous days must involve towering walls of water. Not always. Repeated moderate waves can be plenty. Violence is not only measured by height, it is measured by force, frequency, fatigue, instability, and the bad luck of being knocked down in the wrong place when the next one is already arriving. Piers and breakwalls make matters worse in a particularly nasty way. The NWS safety guidance explains that waves near piers are chaotic because incoming waves reflect off the structure, then combine with new incoming waves to produce even steeper and larger combined waves. The structures themselves are hard rock and concrete, which means the hazard is not just the water, but the surface you may be thrown against if the water has an opinion about your balance. Structural currents flowing along the pier add another layer of danger. This is one of those cases where the built environment does not tame nature, it complicates it. A pier looks like shelter. In heavy weather, it can become a machine for concentrating wave energy and moving water into patterns that are far less forgiving than the open beach a short distance away. That is why the Weather Service repeats such blunt advice about staying well clear of piers. The lake near a structure is not merely rougher, it is less predictable in exactly the ways that matter when people panic. There is another subtle cruelty in violent wave fields, and that is the way they distort judgment. A person looking from shore may see a large breaker and think the danger is contained in that single obvious crest. In reality, the entire water column is in motion. Waves transmit energy, not just foam, and what looks like a dramatic front edge is attached to currents, undertow-like motions, rebounding water, and chaotic intersections that continue after the crest collapses. The Great Lakes beach hazard materials from the Weather Service note that many current-related incidents involve combinations of dangerous currents and high short-period waves. That is why people get into trouble even when they are not swept out in the classic beach movie version of a rip current. They are exhausted by repeated impacts. They are shoved into deeper water. They are moved alongshore into worse locations. They are pinned, tumbled, or stunned. Violent waves do not need to carry you elegantly offshore to be deadly. They only need to prevent you from regaining control for long enough. For vessels, the phrase violent waves means something else as well. The point where motion stops being tolerable and starts becoming structurally consequential. The Great Lakes wave system is important enough that NOAA runs dedicated wave models for the basin, and the Great Lakes Experimental Wave Model issues 3-day forecasts of wave heights throughout the lakes. That forecasting effort exists because wave conditions affect commercial shipping, nearshore flooding, harbour operations and coastal safety across the region. When the NWS Marquette office describes storms with open lake significant waves of 20 to 25 feet and notes that rare peaks can run much higher, it is describing not just an inconvenience to navigation, but sea states capable of overwhelming design assumptions, forcing route changes, endangering ships large enough to make ordinary people feel very small just by looking at them in calm weather. A freighter is an impressive object tied to a dock. In steep November seas, it is still at the mercy of timing heading and the question of whether the next crest arrives at the worst possible moment. Another complication is that the water itself can be physically displaced on a lake-wide scale by strong storms. Michigan Sea Grant explains that intense winds can push water toward one end of a lake, producing storm surge conditions there, while water levels may fall on the opposite end. After the storm passes, the displaced water can slosh back as a seiche. The result is that violent waves may arrive in a setting where the baseline water level has already been temporarily altered, which changes how surf reaches beaches, overtops structures, or attacks bluffs and harbour entrances. And if that sounds like the lake is behaving more like a basin of moving mass than a scenic body of water, that is because it is. A wave is one thing. A whole lake surface tilted by wind and pressure, then rebounding, is something else entirely. Put the two together in late autumn, and you get the kind of shoreline damage and water level chaos that makes local residents stop saying, "The lake is rough," and start saying, "It came up farther than I've ever seen." Occasionally the atmosphere can even generate larger tsunami-like surges on the lakes through rapid pressure changes. NOAA research has documented meteor tsunamis in the Great Lakes, waves caused by sudden atmospheric forcing rather than earthquakes. These can strike shorelines with little warning, and NOAA notes that they can be insidious because they may bounce off the shoreline and return again even after skies appear calmer. They are not the main story in every gale, and they are not needed to make the lakes dangerous in November. The ordinary wave field is fully capable of doing that on its own, but their existence does reinforce the larger point. When the Great Lakes turn violent, there is more than one way for the water to become hazardous. Wind waves, breaking surf, structural currents, seiches, storm surges, and occasionally meteor tsunamis all belong to the same broad lesson. A large freshwater basin under strong weather does not express danger in one tidy form. It expresses it in several at once. So the real answer to when waves turn violent is this. They do so when the wind has had enough speed, enough time, and enough room to load the surface with energy. When the lake geometry allows that energy to build into steep, short-period seas. When the storm reshapes the wind field faster than the water can settle, and when the shore forces those waves to steepen, break, reflect, and combine. Violence on the Great Lakes is not only about size, it is about compression. Energy compressed into short intervals. Water compressed by shoaling. Risk compressed by cold temperatures, changing winds, and narrow margins near shore or in shipping lanes. By the time the spray is blowing over breakwalls and the freighters are disappearing between crests, the transformation is already complete. The lake is no longer simply rough. It is acting with the full force of a season, a basin, and a storm all working together. And once that begins happening often enough over long enough years, the water starts building a second kind of violence too, the one written into wrecks, missing ships, and a maritime history that remembers exactly what these inland seas can do. And once waves have done that often enough in fog, often enough in darkness, often enough against shoals, reefs, sandbars, harbours and hulls built for commerce rather than immortality, the lakes begin to collect a second history beneath the surface. This is the part that gives the region one of its most sobering identities. Not just a corridor of trade, not just a chain of inland seas, but a graveyard of freshwater ships. Historical estimates vary depending on how a wreck is counted and what records survive, but a NOAA technical paper on the Great Lakes wave system notes the Great Lakes Shipwreck Museum's estimate of around 6,000 shipwrecks and roughly 30,000 deaths across the system. Even if one were to argue over exact totals, the larger truth does not budge. These waters have taken an extraordinary number of vessels, crews and passengers over the centuries. That number makes more sense when you remember what the lakes have always been used for. NOAA's Thunder Bay materials describe the Great Lakes as a natural waterborne highway extending deep into the interior of North America, and the US Army Corps of Engineers describes the modern Great Lakes navigation system as a 1,600-mile deep draft network running from Duluth, Minnesota to Ogdensburg, New York. For centuries, people have pushed goods, people, timber, grain, coal, iron ore and machinery across these waters because water transport was efficient, practical and often essential. A place that carries intense traffic for a long time through difficult seasons eventually gathers losses. That is not mystical. That is arithmetic with weather added to it. And weather was never the only problem, though it was often the most dramatic one. NOAA's Thunder Bay Sanctuary history describes northwestern Lake Huron as one of the most treacherous stretches in the Great Lakes system because of unpredictable weather, murky fog banks, sudden gales, and rocky shoals. That list is useful because it reminds us how shipwrecks usually happen in the real world. Not from one villain, but from several inconveniences arriving together with bad timing. A captain loses visibility in fog. The wind freshens faster than expected. A reef or shoal waits exactly where geography says it always has. A vessel under sail or steam fails to clear a hazard. A cargo shifts. Ice forms. Fire breaks out. Another ship appears where no one wanted another ship to appear. Then one event becomes a report and later a memory, and eventually a wreck site visited by divers in very cold water. That is one reason the phrase graveyard of freshwater ships feels earned rather than theatrical. The Great Lakes did not become this by hosting one spectacular tragedy and then politely retiring from the business. They accumulated losses across every era of regional growth. Thunder Bay alone is estimated by NOAA to contain over 200 shipwrecks, and the agency notes that fire, ice, collisions and storms have claimed nearly or more than 200 vessels in and around that part of Lake Huron. Wisconsin's side of the system tells a similar story at a different scale. The Wisconsin Historical Society says the state has roughly 750 Great Lakes shipwrecks, while NOAA's Wisconsin Shipwreck Coast National Marine Sanctuary currently protects 36 known historic shipwreck sites, and notes that many more may still be undiscovered within sanctuary boundaries. In other words, the graveyard is not a single place with a gate and a sign. It is distributed across the basin, from famous wreck alleys to quiet stretches of bottom where a hull rests far from public memory. What is especially haunting about Great Lakes wrecks is how well many of them remain preserved. NOAA repeatedly notes that the cold, fresh water of Lake Huron and Lake Michigan helps preserve shipwrecks exceptionally well. In Thunder Bay, many sites remain nearly unchanged, with masts standing, deck hardware in place, and even personal possessions sometimes surviving. NOAA says the cold freshwater environment inhibits marine organisms harmful to wrecks, and slows the kind of corrosion more common in saltwater. That means the lake floor does not merely swallow ships, it stores them. Time works differently down there. On some deep sites, the vessel is less a scattered ruin than a suspended sentence from another century, waiting in darkness with its shape still legible. That preservation changes the emotional tone of these wrecks. A ship lost in salt water may disappear quickly into collapse, corrosion, and marine life. A ship lost in the Great Lakes can remain disturbingly recognisable. NOAA notes that some sites in Thunder Bay and other lake sanctuaries are among the best preserved in the world, and Lake Huron's cold fresh water has kept many wrecks nearly intact. There is something unsettling in that. It means a wreck can still look like an argument interrupted. The deck fittings are where they were. The hull shape still holds. A mast still rises. You look at the images and realise this is not history reduced to fragments. It is history paused, with the ending understood, but the middle somehow still visible. Of course, ships were not all dying the same death. The lakes wrecked different kinds of vessels in different eras for different reasons. NOAA's sanctuary materials in Thunder Bay describe a collection ranging from pioneer steamboats and wooden schooners to huge steel freighters. Wisconsin shipwreck coasts protected vessels likewise span the 1830s to the 1930s. That variety matters because it reminds us the graveyard grew alongside the technology of the region. Early craft faced the hazards of sail, incomplete charts, limited forecasting, and unforgiving coasts. Later steamers and steel freighters gained power and carrying capacity, but they also pushed farther, longer, and later into difficult seasons. New technology changed the shape of risk, but it did not abolish risk. The lakes adapted quite easily to every new hull form presented to them. It also helps to remember how intense the traffic once was. The Great Lakes were central to the rise of inland commerce, and the volume of movement itself increased exposure to hazard. NOAA's Thunder Bay materials emphasise centuries of exploration, transportation and commerce, while Great Lakes economic analyses describe the region's industries depending heavily on waterborne transportation for raw materials and finished goods. The more vessels you send through fog, storms, reefs, narrow channels and shoulder season weather, the greater the number of opportunities for something to go wrong. Many wrecks were not the product of legendary monsters of weather, but of ordinary commerce meeting ordinary hazard a little too often. A lightly loaded schooner, a bad chart, a hidden shoal, one navigational mistake, and suddenly there is another site for archaeologists to map 100 years later. Fog deserves a moment of respect all by itself. Storms get the songs and the newspaper language, but fog has done quiet, efficient work on these lakes for a very long time. Noah's Thunder Bay descriptions put murky fog banks right alongside sudden gales and rocky shoals as defining dangers of Shipwreck Alley. That is because fog strips away one of a mariner's oldest defences, the ability to see what is coming and where one is in relation to it. On the Great Lakes, where shorelines can be deceptive, reefs can wait in the wrong place, and another vessel may be moving through the same corridor with equal uncertainty. Poor visibility can turn a manageable passage into guesswork, and guesswork on water has always been one of the more expensive habits. Shoals and reefs add a different kind of cruelty because they are so impersonal. A storm can at least be blamed for being in a mood. A shoal is simply doing its job. It remains where geology left it and waits with infinite patience. NOAA's Thunder Bay history repeatedly ties wreck concentration there to rocky shoals, and that makes perfect sense. A ship under weather stress is already losing options. Reduce visibility, increase wind, build steep waves, and suddenly a hazard that was charted, known, and perfectly static becomes fatal because the vessel cannot quite clear it, cannot turn in time, or is driven onto it by force it can no longer manage. There is something almost administrative about such wrecks. The lake submits the paperwork. The rocks process the request. Ice, too, belongs in this history, though it arrives with less drama than a November gale and often leaves damage just as final. Noah's sanctuary accounts include ice among the causes of losses in Thunder Bay, and the agency also notes that ice movement and normal wave action can damage wrecks after they sink, especially in shallow water. For mariners, lake ice has always been a double hazard. Before broad ice cover forms, cold conditions increase icing on decks and rigging, shorten survival times and complicate handling. After ice begins to move, it can crush, trap, or batter vessels and shoreline infrastructure. Winter on the lakes is not a clean freeze that politely halts danger, it is another phase of it. The graveyard contains plenty of reminders that the route from late autumn to hard winter is not a peaceful corridor. One of the most striking regional examples is Thunder Bay itself, which Noah calls Shipwreck Alley for very good reason. The sanctuary is now 4,300 square miles, protects a nationally significant collection of historic shipwrecks, and is estimated to contain over 200 wrecks, with more than 90 located, and others still missing. Some sanctuary materials note that roughly half the ships lost there have not yet been found. That last detail is worth savouring for a moment, in the uneasy sense of savouring. Even in a region already famous for wrecks, there are still losses not fully accounted for, hulls not yet identified, endings not neatly placed on a map. The graveyard is therefore not just historical, it is still being catalogued. It is a museum whose collection continues to emerge from the dark one sonar pass at a time. Wisconsin's side of Lake Michigan offers another version of the same truth. NOAA's Wisconsin Shipwreck Coast National Marine Sanctuary protects 36 known wreck sites in a 962 square mile area, and historical research suggests nearly 60 more shipwrecks may yet be undiscovered there. NOAA also emphasises that these sites are unusually well preserved by Lake Michigan's cold, fresh water and represent vessels central to building the nation between the 1830s and 1930s. So the bottom here is not merely cluttered with broken boats, it is an archive of the industrial Midwest, of grain routes, passenger movement, lumber, steam, sail, commerce, and error. The lake bed, in a sense, is holding the paperwork of a growing continent, except some of the files happen to be full-size schooners. There is a particular sadness in the diversity of those wrecks. Some were workhorses carrying raw materials, some were passenger vessels, some were seasonal traders, some vanished in famous storms, others were simply unlucky in conditions no one would have turned into a ballad. Wisconsin Historical Society materials mention the Rouse Simmons, the so-called Christmas tree ship, which vanished in Lake Michigan in 1912 with cargo, captain, crew, and passengers, and whose lost trees later washed ashore for years. That detail is almost too neat for a writer to invent without being accused of overreaching. Yet it is precisely the kind of detail real shipwreck history produces, not grand symbolism, just ordinary trade interrupted so completely that bits of the cargo keep arriving at shore after the people do not. To maybe why wrecks on the Great Lakes hold the imagination so firmly. They sit at the intersection of labour, weather, geography and memory. A wreck is never only the story of a storm, it is also the story of why the ship was there to begin with, what it carried, what schedule it was trying to keep, what technology it trusted, what coast it misjudged, what forecast it did not have, and what conditions tipped inconvenience into catastrophe. NOAA's sanctuary histories make that plain by treating shipwrecks not as isolated curiosities, but as a cross-section of maritime commerce and travel on the lakes. Each hull on the bottom is a lesson in how the region worked and how the region could fail those working within it. Re is also a moral tone that enters quietly here, though not in a scolding way. The lakes did not become a graveyard because people were foolish in some cartoonishly obvious sense. Most of the time they were doing what societies needed done, moving ore, coal, timber, grain, machinery, livestock, passengers, Christmas trees, or any of the 1,000 other things that make a region function. They were using the natural highway available to them. They were accepting known risks because economies have always leaned on people willing to accept known risks. That does not make the losses less tragic, but it does make them more human. The graveyard below is not full only of reckless adventurers chasing dramatic endings. It is full of working lives interrupted by the fact that the lakes could turn faster, harder, and meaner than plans allowed. Then there is the strange calm of the wrecks now. NOAA describes many deep Great Lakes sites as time capsules. A century-old vessel can rest in remarkable stillness, protected by cold fresh water, its damage visible, its final posture fixed. That calm is part of what makes these wrecks so affecting. They are no longer in motion, no sails are straining, no engines are trying to answer a helm order, no crew is scrambling. The violence happened once, perhaps in a matter of minutes or hours, and then the ship entered another category entirely. A wreck site is the after-image of weather. It is what a gale looks like years later when all the noise is gone and only the evidence remains. When people speak of the Great Lakes as a graveyard of freshwater ships, they are not reaching for a dramatic phrase simply because dark water invites dark language. They are describing a documented historical landscape spread across the inland seas, one preserved unusually well and studied increasingly carefully by archaeologists, historians, and sanctuary staff. Thousands of wrecks, tens of thousands of lives over 200 wrecks in Thunder Bay, 36 protected sites in Wisconsin's shipwreck coast, with more likely undiscovered, and whole categories of vessels preserved by cold fresh water well enough to teach us how they lived and how they died. The bottom of these lakes is not empty, it is crowded with proof. Among all those proofs, one loss has come to stand above the rest in public memory. Not because it was the only one, and not because the lake suddenly became dangerous that year, but because it arrived late enough to feel modern, immense enough to feel impossible, and November enough to sound like a verdict the region had been issuing for generations. The graveyard had been filling for a very long time already. Then one storm and one freighter gave the whole history a single name that people far beyond the Great Lakes would never quite forget. Among all the wrecks resting in those cold inland depths, one name refuses to stay quiet for very long. Not because it was the first great loss on the lakes, and certainly not because it was the only one, but because it arrived late enough to feel modern, large enough to seem almost unsinkable, and public enough to lodge itself in memory far beyond the Great Lakes basin. The Edmund Fitzgerald was launched on June 7, 1958, at Great Lakes Engineering Works in River Rouge, Michigan. At the time of her launch, she was the largest carrier on the Great Lakes. She measured 729 feet long by 75 feet wide, weighed 13,632 tons, and when fully loaded could carry about 27,500 tons. She became a record-setting ore carrier, hauling taconite through the Soo locks and earning nicknames like the Big Fitz and the Pride of the American Flag. Even before her final voyage, she already had the kind of reputation that makes people feel they know a ship the way they think they know a sturdy bridge or a familiar train line. Reliable, proven, not the sort of thing expected to vanish in a matter of minutes. That familiarity matters, because the Fitzgerald was not a romantic relic from the age of sail, drifting around with canvas and luck. She was a modern Great Lakes workhorse. For 17 years she carried taconite from the Minnesota Iron Range towards steel-producing ports farther east and south. The National Weather Service notes that she set major haul records and was considered a vessel sailors were proud to serve on. Captain Ernest M. McSorley, who had more than 40 years of maritime experience and had taken command in 1972, was widely respected as a capable master. The ship itself was well known, the captain was well known, and the route was not some foolish adventure into unknown waters. That is part of why the loss feels so unsettling even now. It didn't happen at the far edge of exploration. It happened in a working system, on a working run, aboard a ship people had every reason to trust. And trust on water can become a dangerous comfort if the weather decides it has other plans. There was, however, one detail sitting quietly in the background before the voyage even began. On October 31st, 1975, during a routine Coast Guard inspection in Toledo, inspectors found that several hatch covers would not close properly. The concern was straightforward. If water washed aboard in quantity, it could leak through those imperfect closures into the cargo hold. On calmer days, that sort of finding might remain an irritating maintenance problem. In severe weather, it belonged to a more serious category. It did not mean the ship was doomed, and it would be dishonest to pretend a single inspection note writes the ending by itself. But it does mean that when people later tried to understand what happened, they were not working from a blank page. They were working from a ship already known to have at least one vulnerability, and that matters in a story where massive seas, heavy cargo, and a sudden disappearance would soon collide with very little mercy. The final voyage began on November the 9th, 1975, at Burlington Northern Railroad Dock No. 1 in Superior, Wisconsin. McSorley loaded 26,116 long tons of taconite pellets, processed iron ore in small hardened pellets, and departed at about 2:30 in the afternoon bound for the Detroit area. Soon after departure, the Fitzgerald was joined by the Arthur M. Anderson, another ore carrier under Captain Bernie Cooper. Because the Fitzgerald was faster, she took the lead, with the distance between the two ships generally running about 10 to 15 miles. The captains were already aware that a November storm was building into the Great Lakes from the plains, and they agreed to take a more northerly route across Lake Superior, closer to the Canadian shore, hoping to gain some protection from the higher land there before later turning southeast toward Whitefish Bay. It was not a reckless route. It was a practical decision made by experienced men trying to use geography in the older sensible way. Keep some land between yourself and the worst of the weather, if you still can. At first, this all still belonged to the category of hard but manageable weather. Gale warnings had been issued on November 9th and were upgraded to storm warnings early on November 10th. The storm itself tracked from the central United States into the Great Lakes and intensified rapidly as it moved northeast. The National Weather Service in Marquette notes that sustained winds of 30 to 45 knots were observed on Lake Superior before the low crossed, with winds later shifting to the northwest and increasing, and 50-knot winds recorded over the eastern part of the lake. The Great Lakes Shipwreck Historical Society describes conditions during the worsening voyage as winds gusting to 50 knots with seas of 12 to 16 feet. Serious conditions, but still ones both captains had experienced before. That detail is important. No one on either bridge was looking out at the first bad wave of his career. This was dangerous weather, yes, but still the sort of danger Great Lakes mariners had known how to face many times before, which is one reason the ending still feels so abrupt. Experienced people can survive severe weather over and over again, right up until one arrangement of wind and water finally becomes the wrong one. By early afternoon on November 10th, the pattern had begun to change in ways that would matter terribly. The Fitzgerald had passed Michipicoten Island and was approaching Caribou Island. Captain Cooper of the Anderson later maintained that he watched the Fitzgerald pass alarmingly close to 6 Fathom Shoal, north of Caribou Island, close enough that he and his officers believed she had gone right across dangerous shallow water. Whether that moment directly damaged the ship remains disputed, but it stayed central to later theories because it offered a possible mechanism for hull damage at exactly the wrong time. Then, at about 3:30 that afternoon, McSorley radioed Cooper with the kind of message no trailing captain likes to hear from the ship ahead. He reported that he had a fence rail down, had lost or damaged 2 vents, and had taken on a list. He also said both pumps were running, and asked the Anderson to stay by him until he reached Whitefish. That is one of the most haunting moments in the whole story, because it is not yet panic. It is controlled trouble. The ship is damaged, the captain knows it, and he is still trying to get her to shelter under his own command. The afternoon became a narrowing corridor. The storm's track turned out to be more adverse than anticipated, and as the low moved across Lake Superior, the wind shifted behind it. What had been a plan to ride a northeasterly gale closer to the North Shore turned into a much worse arrangement, once the wind swung around and began building waves along the wide west-to-east reach of the lake. National Weather Service materials explain that as the two ships turned southeast toward Whitefish Bay around midday, the backside of the storm brought strengthening northwest winds, allowing larger waves to build across the lake. By around 4 p.m, the Fitzgerald had lost her radar antenna in the storm and had to rely on the Anderson for navigational guidance. That meant the trailing vessel was now feeding radar fixes forward to the damaged ship ahead, trying to help her keep clear of other traffic and hold her way towards safety. It is one of those details that makes the whole event feel painfully intimate. Two freighters in a darkening gale, one increasingly crippled, the other trying to talk her through the weather mile by mile. Meanwhile, the lake was reaching the worst part of its own arrangement. The later weather reanalysis, summarised by the NWS, found that there was about a 6-hour period during the storm when conditions were especially intense, and that interval lined up with the Fitzgerald's final hours. By 4 p.m, model reconstructions indicated sustained winds of roughly 45 to 50 knots across southern Lake Superior. Near the time of the sinking, the Anderson reported gusts reaching 75 knots. The same reanalysis suggests significant wave heights around the Fitzgerald may have risen to roughly 25 feet, with maximum waves possibly approaching 40 feet. The important thing here is not only that the weather was severe throughout the storm, it is that the ship appears to have entered the most intense pocket of the event at the very time she was already reporting damage and a list. Weather does not need to be uniformly catastrophic across an entire lake to destroy a vessel. It only needs one ship to arrive at one very bad patch while already compromised. Around 5:20 p.m, conditions were bad enough that a wave smashed the Anderson's starboard lifeboat and made it unusable. Cooper reported steady winds of 58 knots, with gusts to 70 and seas of 18 to 25 feet. At about 6:55 p.m, according to his later account, the Anderson was struck from astern by an enormous wave that surged along the deck and drove the bow down hard into the sea. Cooper believed that one or two great waves like those then ran on toward the Fitzgerald. That part is interpretation, not proof, and it is only fair to leave it in that category. But even without adopting his conclusion, the account tells you what kind of lake the Anderson was inhabiting by then. This was no longer a vessel riding out a stiff blow. This was a ship being physically overrun by water of exceptional force, while darkness and spray further narrowed everyone's field of understanding. There are moments in maritime disasters when explanation grows harder, because the environment itself starts removing witnesses, visibility, instruments, and confidence all at once. This was one of those moments. The last exchange came at about 7:10 p.m. The Anderson's first mate, Morgan Clark, was using radar to help track the Fitzgerald relative to other vessels near Whitefish Point. Sea return, the interference caused by heavy seas, was already making the radar picture unreliable. Clark asked whether the Fitzgerald had checked down in speed. McSorley said yes. Clark gave him information about a target ahead and answered his question about whether he would clear it. Then Clark asked the question that has echoed for decades. "How are you making out with your problems?" McSorley replied. "We are holding our own." 4 words, calm enough to sound almost routine, and therefore more unsettling than anything flamboyant could have been. A man in trouble but still in command, still speaking as though the ship was hurt but moving, strained but not lost. Minutes later, around 7:15 p.m, the Fitzgerald disappeared from the Anderson's radar. Clark called again at about 7:22. There was no answer. No distress call had been sent. That absence of a distress call has always been one of the most chilling parts of the event. It suggests not a slow surrender, but a rapid end. Search efforts began that night, though even that simple phrase fails to capture what searching meant under those conditions. The Anderson became the primary vessel in the search, though Captain Cooper warned the Coast Guard that the seas were tremendously large and that turning back out would mean taking a severe beating for very little forward progress. Even so, the Anderson went back. She and other vessels found the Fitzgerald's lifeboats and debris, but no survivors. The Coast Guard launched aircraft and dispatched cutters. No bodies were ever recovered. There is something terrible in how quickly an industrial object can move from present tense to aftermath. At 7:10 there is radio traffic. At 7:15 there is radar loss. Before long there are only floating objects, and the realization spreading ship to ship that the 729-foot ore carrier ahead has gone somewhere no one on the surface can follow. The wreck itself was located on November 14, 1975, when a US Navy aircraft equipped with a magnetic anomaly detector identified a strong contact about 17 miles north-northwest of Whitefish Point. Over the next several days, the Coast Guard cutter Woodrush located 2 large pieces of wreckage in about 535 feet of water. In May 1976, a Navy underwater recovery vehicle photographed the wreck, and the stern section clearly showed the name Edmund Fitzgerald. By then, the lake had already done what it often does after violence. It had become quiet again, keeping the proof below. The ship lay in 2 main sections on the bottom, and the event entered that strange Great Lakes category in which the weather has ended but the argument about the cause is only beginning. Shipwrecks sometimes feel like conclusions from shore. Underwater, they are often evidence waiting to be interpreted. An interpretation, in this case, has never settled into one clean answer. The Coast Guard concluded that the most probable cause was loss of buoyancy and stability from massive flooding of the cargo hold, with water entering through ineffective hatch closures as seas came aboard the deck. It also allowed that additional damage may have occurred if the ship had grounded near Caribou Island. The National Weather Service summary says the Coast Guard believed the ship sank abruptly, and the damaged lifeboat suggested they were never launched. The Great Lakes shipwreck. Historical Society, however, emphasises that there is no conclusive evidence establishing a single definitive cause, and notes that competing theories remain active, including the possibility that the Fitzgerald dove bow first into an enormous sea after already losing buoyancy. The honest answer, then, is not that the mystery has been neatly solved. It is that several plausible factors seem to have converged: heavy weather, a damaged or vulnerable ship, possible flooding, perhaps possible shoal contact, and waves arriving at the worst possible angle and moment. Sometimes history gives you a courtroom ending. Sometimes it gives you a case file with seawater on it. That, I think, is why the Fitzgerald still holds people so firmly. She was large, modern, experienced, radio-equipped, radar-guided by another ship, and still gone in minutes. The loss of all 29 crewmen turned her sinking into more than a weather story or a shipping story. It became a regional warning written in steel, not because it proved the lakes were uniquely malicious, but because it demonstrated how quickly a Great Lakes storm could still outrun strength, size, and professional skill. The NWS still describes the Fitzgerald as the largest ship ever to sink on the Great Lakes. The event sits in public memory not only because of the tragedy itself, but because it stripped away any remaining temptation to think of these waters as merely oversized lakes with a seasonal temper. By the time the Fitzgerald vanished, Lake Superior had already made its point. The only thing left was for everyone else to learn from it, and that is where the next part of the story naturally begins. Because after a ship like that disappears in 1975, the obvious question is what changed in the way we watch, forecast, and warn. What changed after losses like the Edmund Fitzgerald was not the weather, of course. Lake Superior did not glance guiltily at the wreck reports and decide to tone things down for future generations. The wind still crosses open water with the same old confidence, cold air still drops south, and November still knows how to line up its worst habits. What changed was our ability to watch the lakes in real time, to model what they are likely to do next, and to turn all of that information into something a captain, a harbour master, a ferry operator, or even a cautious person standing on a pier can actually use. Today, forecasting the Great Lakes is not one single act performed by one heroic meteorologist staring into the middle distance. It is a layered system. NOAA says marine forecasters now combine observations from automated stations, buoys, ships, upper air soundings, aircraft, satellites and radar with guidance from weather, wave, and oceanographic models, then apply their own expertise to build forecasts out to 5 days. That last part matters. The models are powerful, but the forecast still has human judgment in it, which is reassuring, because if there is one thing weather enjoys, it is making computers look briefly overconfident. The first layer in that system is simple observation. Before anyone can predict what the lakes are about to do, they need to know what the lakes are doing right now. That sounds obvious, but on a region this large it is no small task. NOAA's Great Lakes Observations pages collect current data on wind speed, wave height, water temperature, pressure, and air temperature across the 5 lakes. NOAA GLAIL also runs a real-time marine observations page that gathers data from buoys, coastal meteorological stations, airports, ships, and other reporting platforms. Those observations include wind speed and direction, gusts, air temperature, dew point, pressure, water temperature, wave height, wave period, and even live tracking of Great Lakes ship locations, with updates arriving hourly. There is something rather comforting in that. A century ago, a captain in worsening weather might have had little more than a barometer, the look of the sky, and a strong preference for optimistic thinking. Today the lakes are watched continuously by instruments that never get tired, never misread a cloud out of pride, and never say, "It seems fine to me," while everything around them is clearly becoming not fine at all. Water level monitoring is another quiet revolution. NOAA's Centre for Operational Oceanographic Products and Services maintains Great Lakes water level stations as part of the National Water Level Observation Network, and NOAA says those real-time water level measurements are updated every 6 minutes. The same system provides the datums used for charting and navigation, including the International Great Lakes datum. That sounds like dry administrative work, and in a sense it is, but dry administrative work has saved many people from wet and highly regrettable circumstances. On the Great Lakes, where storm surge, seeches and short-term water level changes can matter enormously near harbours and shorelines, knowing the level of the water is not a luxury. It is part of understanding how the lake is responding to wind and pressure in the moment. If a strong storm is piling water toward one end of a basin or pulling it away from another, those measurements become part of the operational picture. And on these lakes, the operational picture is often the difference between a difficult passage and a very expensive lesson. Then there is radar, which has changed the rhythm of forecasting in ways so ordinary now that we sometimes forget how extraordinary they are. NOAA's radar system displays real-time radar on a map, together with alerts and forecasts, and the Great Lakes Programme pages link directly to regional radar views as part of their observation and forecasting suite. Radar is especially useful for tracking precipitation bands, frontal structure, snow squalls, and rapidly evolving thunderstorm hazards over and around the lakes. It cannot tell you everything about the lake surface, of course. Radar is not peering lovingly into the soul of every wave, but it does give forecasters and mariners a much clearer sense of where organised weather is, how it is moving, and where it is intensifying. That is no small thing on waters where squalls, snowbands and convective bursts can sharply reduce visibility or briefly drive winds well beyond whatever pleasant assumptions the morning forecast inspired. A sailor who once might have relied on the horizon alone now has access to a moving picture of what the sky is organising overhead. Satellites have made the picture broader still. NOAA Coastwatch's Great Lakes node provides near real-time environmental data and products for the lakes, including satellite-based surface temperature imagery, true colour views, and ice products that monitor ice type, thickness, and cover. Coastwatch also notes that its data are used to track wind, plumes, ice cover, and physical parameters such as waves and currents. This matters because the lakes are too large and too variable to be understood only from scattered points. Buoys tell you what is happening where they are. Satellites help show patterns across the whole basin. They reveal temperature contrasts, open water areas, ice growth, and broader surface conditions that a single station cannot capture. There is something satisfying about that combination. One system listens closely at fixed points, another looks widely from above. Forecasting the lakes today is, in large part, the art of making those perspectives talk to each other, and when they agree that something unpleasant is taking shape, Wise people start adjusting plans before the shorebirds do. Of course, observations alone are not enough because they tell you what is happening now more readily than what will happen next. That is where numerical models come in. NOAA says its operational forecast system is built from the automated integration of observing data streams, hydrodynamic model predictions, product dissemination, and continuous quality control. These systems produce nowcasts, which are scientific predictions of present or near-present conditions using recent observations, and forecasts, which extend those predictions into the future using modelled weather and hydrologic forcing. In other words, the models do not merely describe the lakes as they are. They use the current state of the lakes, the atmosphere, and related inputs to estimate how water levels, currents, temperatures, and other conditions will evolve over the next hours and days. That is a very modern kind of foresight. It is not prophecy, and it does not pretend to be. It is disciplined approximation, updated constantly, corrected continuously, and vastly better than looking at a grey horizon and deciding the wind has an honest face. Across the 5 Great Lakes, that modern hydrodynamic system now operates under what NOAA describes as the Great Lakes Operational Forecast System, or GLOFS. NOAA GLERL explains that GLOFS is a publicly available, automated, model-based system designed to improve predictions of water levels, currents, temperatures, and related conditions for commercial, recreational, and emergency response users. It uses current lake conditions and predicted weather patterns to forecast conditions up to 5 days or 120 hours into the future. NOAA also says the National Weather Service and the National Ocean Service run GLOFs together on NOAA's high-performance computing system, which gives the models direct access to operational meteorological products needed for timely forecasts. That is a long way from a captain leaning into sleet and wondering whether the barometer has started dropping with genuine intent or simply has a pessimistic personality. The lake is now modelled as a living system, continuously ingested into computers powerful enough to simulate water motion, temperature structure, and ice behaviour across enormous basins. The details become even more impressive when you look at the lake-specific systems. Lake Superior has the Lake Superior Operational Forecast System, or LSOFS. Lake Erie has LEOFS. Lake Michigan and Lake Huron are handled together in LMHOFS, which makes sense because those 2 lakes are connected hydrologically at the Straits of Mackinac. Lake Ontario has LOOFS. NOAA says these systems use the finite volume community ocean model, coupled with a sea ice model, to generate nowcasts and forecasts of water levels, currents, water temperature, ice concentration, ice thickness, and ice velocity. They update 4 times per day and run out to 120 hours. The Lake Superior and Lake Erie information pages also note that these models are forced by operational meteorological products, including the high-resolution rapid refresh model for nowcasts and forecast products, such as the National Digital Forecast Database for future forcing, which is really just a very technical way of saying the forecast system is not built from one isolated guess. It is built from an ecosystem of weather and water guidance, constantly cross-feeding information into the next set of decisions. That term nowcast deserves a moment, because it sounds faintly like something a startup would invent and then explain too enthusiastically over coffee. In practice, though, it is very useful. NOAA defines a nowcast as a scientific prediction of the present and near-present state of a water body that incorporates recent observed meteorological and oceanographic data, including gridded products where direct observations are not available. A forecast then grows forward from that nowcast. That means forecasters are not starting blind every time a new model cycle begins. They're initializing from a best estimate of the lake as it is now, with all the latest observations folded into the setup. On the Great Lakes, where short-term water level oscillations, currents, surface temperatures and ice conditions can change quickly and matter immediately, that is extremely valuable. You're not merely asking what the lake might do tomorrow, you're first asking what it is doing right now in all the places you cannot physically observe at once. That is a much better question, and modern forecasting systems are much better at answering it than their predecessors were. Waves, meanwhile, have their own forecasting machinery, because waves are too important to be left as a side note beneath the wind line. NOAAGLERLs. Experimental Wave System, built from WaveWatch 3 and based on the operational Great Lakes Wave Framework available through weather.gov, runs twice per day and produces 3-day forecasts of wave heights across the lakes. NOAA says the experimental version includes an ice wave damping scheme intended to improve estimates when ice cover is present, and it uses HRRR winds for the first 48 hours and GFS forcing afterward. The broader Great Lakes portal provided by the National Weather Service also includes graphic layers for wave height, wind gusts, and air temperature. This means that modern Great Lakes forecasting no longer asks mariners to translate wind speed into wave danger entirely on their own. The wave field itself is modelled and visualised, because everyone involved has by now learned the obvious lesson. On these lakes, the surface is not a secondary concern. It is the concern that tends to hit things. But all of this computing power would not be nearly as useful if the finished forecast were delivered in some form that only graduate students, retired radio engineers, and unusually motivated gulls could decode. So NOAA and the National Weather Service turn the data into operational products people can actually use. The Great Lakes Open Lake Forecast is issued by 5 primary weather forecast offices and covers the waters beyond 5 nautical miles from shore. Nearshore forecasts are issued by local offices responsible for particular coastal stretches. NOAA's Marine Services pages also note that coastal and Great Lakes forecasts are subdivided by zone, each identified by a specific description and code. That zoning matters because conditions on the Great Lakes are not evenly distributed. The north half of one basin may be handling the weather quite differently than the south end, and a sheltered nearshore strip may be experiencing something very different from the open lake beyond it. One giant blanket forecast would be tidier, but tidiness is not the point. Specificity is. Mariners do not need poetry from the Weather Service. They need to know which slice of water is about to become unreasonable. Warnings are the sharp edge of that communication. NOAA's marine weather pages explain that the National Weather Service issues watches, advisories, and warnings for hazardous winds and sea conditions, along with products for dense fog, freezing spray, and other marine hazards. The marine message list includes gale warnings, storm warnings, hazardous seas warnings, heavy freezing spray warnings, dense fog advisories, and small craft advisories, among others. NOAA's Marine FAQ further defines a gale warning as sustained winds or frequent gusts from 34 to 47 knots, and a storm warning as 48 to 63 knots. There is also a hazardous seas warning for wave heights, or steepness meeting locally defined criteria, and a heavy freezing spray warning when conditions can accumulate dangerous ice on a vessel. That last one is especially Great Lakes in character. It is not enough here for the wind to push the lake into violence. Sometimes the spray itself begins trying to turn the ship into a heavier, less cooperative version of itself. Modern forecasting accounts for that too, because the lakes have a gift for making one hazard arrive carrying 2 or 3 friends. Then there is dissemination, which is a wonderfully practical word for the business of getting urgent information into places where urgent information is needed. NOAA, weather radio, broadcasts official forecasts, watches, warnings, and hazard information continuously, 24 hours a day, 7 days a week. NOAA's Marine Radio Information page says the network continuously broadcasts local and nearshore marine forecasts, real-time observations from buoys and coastal meteorological stations, and, where feasible, offshore and open lake forecasts as well. The Weather Service also provides US Coast Guard marine weather broadcast information through its Marine Services branch. So the forecast is not trapped on a website waiting for someone to remember a password and a charger cable. It goes out over radio, into marine communication networks, into text products, and into specialised services that mariners can access at sea. Forecasting is only half the problem. The other half is making sure the person in the weather actually receives the warning before the weather decides introductions are over. One of the quieter strengths of the modern system is quality control. NOAA notes that official real-time products and forecast guidance from systems such as LEOFS and LSOFS are monitored continuously by the Continuous Operational Real-Time Monitoring System, or CORMS, which runs around the clock to help ensure the availability, accuracy and quality of water level, current and related marine environmental information. That may not sound dramatic enough for a bedtime documentary voice, but it is the sort of sentence one should say with appreciation. Forecasting the Great Lakes is not just about producing maps and hoping for the best. It is about monitoring sensors, checking data streams, identifying invalid values, updating model cycles, and keeping the whole chain trustworthy enough that mariners are willing to act on it. A beautiful model that quietly swallows bad data is not much comfort to anyone trying to make harbour before midnight. The unglamorous work of quality control is part of why modern marine forecasting is meaningfully safer than the old days of educated suspicion and damp guesswork. And yet, for all this sophistication, it is worth remembering what forecasting can and cannot do. It can tell you a great deal more than it once could. It can show wind, wave height, water levels, currents, temperatures, ice cover, radar echoes, satellite signatures, and warning thresholds in ways earlier mariners could scarcely imagine. It can update repeatedly through the day and ingest data from the lakes themselves, instead of treating the basin as a blank blue shape on a larger weather map. But forecasting does not calm the lake. It only reveals the lake more clearly. It narrows uncertainty. It improves timing. It gives people more margin to act wisely. That is a tremendous achievement, and it has saved lives. It is not, however, a victory over November. The atmosphere remains free to intensify a little faster than expected, to shift the wind awkwardly, to sharpen a wave field in the wrong corridor, or to cover a vessel in freezing spray while the forecast still reads uncomfortably accurate. Which is why, even now, even with satellites overhead and supercomputers working in shifts, the month still carries that old reputation among mariners. The tools are better, the respect remains. So if you stand beside the lakes today and open the forecast, what you are really seeing is the result of many layers of attention. Instruments on buoys and shore stations, water level gauges updating every 6 minutes, radar scanning precipitation and squalls, satellites mapping the basin from above, hydrodynamic models projecting currents, levels, temperature and ice, wave models estimating how the surface will answer the wind, human forecasters reading all of it, comparing guidance, writing zone forecasts and issuing warnings in language mariners know how to use. It is a far more watchful system than the one that existed half a century ago, and it has made the lakes more legible than they once were. But legible is not the same thing as harmless. We can see November better now. We can measure it better, model it better, broadcast it better, and react to it faster. Still, the reason all that machinery exists is the same reason people on these waters keep listening so carefully when the forecast turns serious. Because even now, with all our instruments and maps and model grids, the gales of November still have a way of making grown professionals speak a little more quietly. For all the improvements in forecasting, radar, buoy data, model guidance, satellite imagery and radio warnings, November still frightens people who know these lakes well, because knowledge does not cancel exposure. It helps, of course. It gives crews more time to decide, more time to reroute, more time to head for shelter or delay departure. But it does not warm the water, flatten the waves, widen a harbour mouth, or make a damaged vessel easier to handle in darkness. That is the first thing to understand about maritime fear in November. It is not superstition. It is not a regional habit of dramatising the weather for entertainment. It is professional respect for a month that takes already large lakes and strips away much of the margin people normally rely on. The forecasts are better. The consequences of getting it wrong remain very old-fashioned. A mariner in November is not only thinking about whether the wind will rise above gale force. That matters certainly, but it is only one piece of the calculation. They are also thinking about water temperature, because cold water changes the meaning of every accident. The National Weather Service warns that warm air can create a false sense of security near lakes and oceans, and that plunging into cold water of almost any temperature can become dangerous if a person is not prepared for what sudden exposure does to the body and brain. Cold shock can trigger dramatic changes in breathing, heart rate and blood pressure, and the Weather Service notes that the involuntary gasp and rapid breathing alone create a serious risk of drowning, even for confident swimmers in calm water. In rough open water, that risk increases. That means a fall overboard in November is not simply a mobility problem. It is immediately a breathing problem, a judgment problem, and often a survival problem within moments. Mariners know that, and it changes the emotional tone of every decision they make. What makes this even crueler is that the body does not wait politely for a person to compose themselves. The same NWS guidance explains that cold shock can be severe in water temperatures of 50 to 60 degrees Fahrenheit, and that gasping or rapid breathing can be triggered by water as warm as 77 degrees. Physical incapacitation can begin within seconds, with weakness, exhaustion, and loss of muscular control in the fingers, hands, arms, and legs, making self-rescue increasingly difficult. That is one of the main reasons life jackets remain so central in every piece of cold water advice. The Weather Service says flotation can create the extra time needed for help to arrive or for a person to get out of danger. So when mariners fear November, they are not just fearing the storm as an abstract event, they are fearing the consequences of a single slip, a single rogue movement, a single failed line, ladder, hatch, or deck step in a month, when the water is ready to punish even very small mistakes. This is also why Coast Guard-style advice sounds so repetitive and so practical. The recommendations are never glamorous because the problem is never glamorous. The Coast Guard urges boaters and fishermen in colder conditions to wear a life jacket, dress for the water rather than the air, carry extra clothing, use at least 2 reliable forms of communication, and have working GPS or charts that mark hazards. That advice may sound almost disappointingly ordinary, but that is because the danger itself is brutally ordinary. Things go wrong fast on cold water. Cell service may fail, batteries may die, visibility may collapse, hands may stop working properly, and the gap between uncomfortable and critical may be only a few minutes wide. November terrifies mariners because it compresses time. It does not always give people the long, graceful window in which to understand that they are in trouble and then solve it at leisure. The water itself is a major part of that compression. NOAA notes that the Great Lakes experience many of their most significant storms and large wave events during the colder months of late fall through winter, and that shore ice later in the season acts as a buffer against wave energy. In November, that buffering is usually not there yet. The surface is open, the wind has room to work, and the lakes are still capable of releasing heat and moisture into the atmosphere, while also building powerful seas. That means the month combines 2 bad qualities at once: the open water reach of autumn and the storm intensity of the cold season. A mariner looking at a November forecast is not merely asking whether it will be windy. They're asking what the lake will become once that wind has miles of exposed water to shape. And what the lake becomes can be deeply exhausting even before it becomes catastrophic. The Weather Service's Great Lakes Safety Guidance notes that Great Lakes waves tend to come in rapid succession, around every 3 to 4 seconds on average in summer conditions, and that repeated waves wear people down quickly. It points out that 225 waves can hit in just 15 minutes if the period averages 4 seconds. That guidance is aimed at beach safety, but the core lesson applies more broadly. Short period waves deny rest. They do not let the body reset between impacts. They hammer. They force repeated adjustments, They wear down balance, judgment, and stamina. Mariners fear November because by then the lake is capable of producing exactly that kind of relentless surface, only larger, colder, darker, and far more consequential for anyone handling a vessel rather than splashing near shore. The danger is not only in the size of the wave, it is in the lack of mercy between one wave and the next. Shoreline hazards reinforce the same point. The Weather Service says dangerous currents and breaking waves are common in the Great Lakes region, and that if whitewater is visible, waves are at least about 3 feet, and dangerous currents may also be present. Another NWS page notes that 85% of current-related incidents occur when waves are 3 feet or greater, and that many such incidents happen near piers and breakwalls. Again, these are public safety messages for people at beaches, but they tell you something important about the character of Great Lakes water. It does not need to reach cinematic heights to become dangerous. Moderate wave conditions, if they are steep, breaking, and repetitive, can already create currents and impacts strong enough to injure, exhaust, or drown people. Mariners understand this instinctively. They do not need a wave to look legendary before taking it seriously. November frightens them because it is the month when serious enough arrives quickly and then keeps building. Visibility is another reason the month retains its reputation. NOAA's marine warning definitions include a dense fog advisory for widespread or localized fog reducing visibility to regionally defined limits not exceeding 1 nautical mile. A nautical mile may sound generous when described from a comfortable chair indoors. On cold water, in traffic, at night, around shoals, lights, buoys, harbour approaches or crossing routes, it is not generous at all. It is a warning that the lake is reducing the distance at which a person can make decisions that matter. Visibility loss on the Great Lakes is not always as dramatic in public memory as towering waves, but mariners know very well that poor visibility multiplies every other hazard. It shortens reaction time, it complicates navigation, it makes traffic separation harder, it makes finding aids to navigation slower and less certain. And if something does go wrong, it makes finding the people involved much harder. Freezing spray adds a particularly ugly layer because it turns the weather into a weight problem. NOAA's marine warning guidance defines a heavy freezing spray warning as an accumulation of freezing water droplets on a vessel at a rate of 2 centimeters per hour or greater, caused by some combination of cold water, wind, cold air temperature, and vessel motion. That is one of those definitions that sounds technical until you picture what it means in practice. A vessel moving through cold, rough water can begin collecting ice on railings, decks, lines, superstructure and equipment. The ship or boat is still trying to handle wind and waves, but now is also getting heavier and less balanced in exactly the places where added weight is least welcome. Mariners fear November because a storm does not always arrive alone. Sometimes the wind, the sea and the temperature collaborate to make the vessel itself worse at being a vessel. The communication problem matters too, and professionals know it. The Coast Guard's cold weather boating guidance recommends at least 2 reliable forms of communication, specifically pointing out that cell phones alone may not be sufficient on the water. It also emphasises a VHF radio, a personal locator beacon, GPS, and local charts. That is not because the Coast Guard enjoys making people carry more equipment. It is because November is a month in which the simplest assumption, we'll call if we need help, becomes less reliable. Batteries drain faster in cold conditions. Water and motion are unkind to electronics. Cell coverage over open water is uneven. A person struggling with cold shock or reduced dexterity may not manage fine motor tasks well. All of that means fear in November is not just fear of the storm itself, it is fear of becoming hard to locate, hard to hear, and hard to reach once the storm has started rearranging the situation. And reaching people on the Great Lakes is no small matter, even when everything works as designed. The US Coast Guard Great Lakes District covers operations across the 5 lakes, the St. Lawrence Seaway, 6,700 miles of shoreline, and 1,500 miles of the international border with Canada, while carrying out search and rescue, maritime safety, aids to navigation, and icebreaking missions. That scale is impressive, but it also illustrates the basic problem. The lakes are vast, distances are real, the weather is often moving. A distress case on such waters is not the same thing as an ambulance call a few streets over. Help may be highly professional and fully committed, but it still has to travel through the same darkness, cold, wind and spray that created the emergency in the first place. Mariners know this. Knowing that rescue exists is reassuring. Knowing how much lake lies between you and rescue is sobering. Another reason November still unsettles mariners is that the month can look less dangerous than it really is, at least at first. The Weather Service notes that warm air can produce a false sense of security around cold water, and that is especially relevant in shoulder season weather, when a relatively mild afternoon on shore tempts people to think the lake has received the same memo. It has not. The air can feel manageable, the water can still be deadly, the sky can look merely grey, the fetch can still be long enough to build hard seas a little farther out. The harbour can still feel close on a chart while becoming annoyingly difficult to reach in real life. Mariners fear November partly because it is deceptive. Midwinter at least announces itself bluntly. November sometimes smiles first, and then asks for a level of seriousness that some people have not yet emotionally unpacked from summer. The timing of the month contributes to that unease as well. The northern Great Lakes can begin seeing ice as early as late November or early December, but Noah Galel notes that broader ice growth historically occurs in January and February. In other words, November often gives mariners the cold season atmosphere before it gives them the cold season surface damping that ice can later provide in some areas. It is a transitional period in the least comforting sense. The lakes are still open enough for full wave growth and normal navigation, but the air is increasingly willing to produce the kinds of conditions associated with winter. That leaves people operating in a gap between seasons, where the open water invites activity, and the weather punishes it with very little patience. No wonder the month keeps its reputation. It combines access with danger in a way that later winter does not always do. There is also the historical memory of November, and mariners are not immune to that. This is not fear based on ghost stories told to frighten apprentices. It is fear reinforced by repeated evidence, by famous losses, by less famous losses, and by the accumulated professional knowledge that the month has been bad in similar ways for a very long time. The forecasting has improved, vessel design has improved, communication has improved, but the recurring late fall setup remains recognisable. Stronger storms, colder air, open water, large waves, poor visibility, and very unforgiving immersion conditions. A mariner does not need to be sentimental about history to take that pattern seriously. They only need to have read enough reports, listened to enough older crews, or spent enough seasons on the lakes to know that November is when a manageable voyage can become a survival problem in distressingly little time. That is why even recreational users get very plain advice. The NWS says to check the official forecast before going out, stay aware of wave and current statements, and remember that most Great Lakes beaches are unguarded. The Coast Guard says wear the life jacket, carry redundant communications, and tell someone your float plan. These are not the instructions issued for a body of water that merely wants admiration. They are the instructions issued for a place where being prepared is often the only difference between an incident and a fatality. Professionals hear the same lesson at a larger scale. The vessel may be stronger, the radios better, the route more formal, the cargo more important, but the underlying rule does not change. November narrows the buffer between routine operations and emergency response. That is why people who work the lakes talk about the month with a different tone than people who simply photograph it. And perhaps the deepest reason November still terrifies mariners is that it attacks confidence from several angles at once. The air is colder, the water is more dangerous, the waves are more relentless, visibility can be reduced. Freezing spray may begin building where no extra weight is welcome. Rescue takes time over large waters. communication can fail at the moment it matters most. The same forecast that sounds like an inconvenience on land can mean something very different 10 or 15 miles offshore. Each individual risk is understandable. Together they create a month in which human control feels thinner. That feeling is not panic. It is not weakness. It is the correct response to a system in which many small setbacks can combine quickly and in a very unfriendly order. Mariners fear November because November is efficient at stacking problems. So even now, with excellent forecasting, continuous observation, modern communications and highly capable rescue services, the month keeps its authority. Not because nothing has changed, but because the basic arithmetic of exposure has not. Open water, plus strong cold season storms, plus cold immersion risk, plus steep repetitive waves, plus reduced visibility still adds up to something severe. In a sense, that is what separates respect from romance. People on shore may admire the sound of November surf, the slate-coloured water, the spray rising over breakwalls, and the freight traffic moving under low skies. Mariners are entitled to a less decorative view. They know that beauty on the lakes is often only the public face of a very strict set of physical rules. They do not fear November because they misunderstand it. They fear it because they understand it too well. And once you see that clearly, the month starts to mean something larger than weather alone. It becomes a way of talking about limits, about what nature allows, about what it does not forgive, and about why these inland seas continue to command such careful respect even from the people who know them best. So what do the gales of November really mean? After all the pressure maps, the cold fronts, the fetch, the wave heights, the wrecks, the forecasts, and the long list of practical reasons not to take these waters lightly, that question turns out to be less sentimental than it sounds. Because the answer is not just that November is stormy. Plenty of places are stormy. The answer is that the Great Lakes are one of the largest surface freshwater systems on Earth, holding about 84% of North America's surface fresh water and about 21% of the world's surface fresh water, while also functioning as a major inland navigation corridor rather than a distant, empty wilderness. The US Army Corps describes the Great Lakes Navigation System as a 1,600-mile deep draft network running from Duluth to Ogdensburg. In other words, the gales of November matter because they strike not some abstract body of water, but a vast freshwater system that is economically useful, heavily travelled, and large enough to behave like a sea when the season lines everything up in the wrong order. That makes the phrase mean something very practical before it means anything philosophical. It means that for a few crucial weeks each year, the lakes become especially good at turning ordinary weather ingredients into serious marine danger. The water is still carrying the stored heat of the warmer months. The air over the continent is cooling rapidly. Stronger cold season storm systems begin moving through the region more often. The lakes are still mostly open, so wind has room to build waves, and the water can keep feeding heat and moisture into the air. National Weather Service reviews of major Great Lakes November storms, including the 1975 Fitzgerald storm and the November 1998 storm that followed a broadly similar track, show how quickly late autumn lows can intensify and how severe the resulting winds and waves can become over the basin. So the gales of November mean seasonal timing as much as raw force. They are what happens when the atmosphere turns aggressive before the lakes have lost their autumn energy. They also mean that language can be misleading. A lake sounds manageable, a lake sounds local, a lake sounds like a place where the biggest hazard is overestimating your ability to build a campfire while holding a paper cup of cocoa. The Great Lakes have always exposed the weakness in that assumption. They are inland only in the geographic sense. In physical behaviour, they can generate strong winds, steep waves, storm surge-like water level changes, seeches, heavy freezing spray, and visibility problems that have far more in common with marine conditions than with the ordinary idea people carry around when they hear the word lake. That is why the gales of November mean a kind of correction. They correct the habit of underestimating familiar landscapes. They remind people that a place can be domestic in summer and fully operational as a hazard in late autumn, without ever changing its name. In that sense, the gales mean that scale is never a cosmetic detail. The Great Lakes are large enough to create their own rules for weather and navigation. They offer the wind-long fetch, the storm track favourable geography, and vessels long exposures far from immediate shelter. Once a strong low sets up over the basin, the result is not merely bad weather on a lake. It is a system of interacting forces unfolding over hundreds of miles of water and shoreline. That is why the region has invested so heavily in navigation infrastructure, forecasting, wave guidance, and water level monitoring. It is also why generations of mariners learned the hard way that large freshwater is not a watered-down version of the sea. Freshwater may preserve wrecks better, but it does not treat them any more kindly on the way down. The gales also mean memory. Not memory in a mystical sense, but in the very practical sense that regions learn from repetition. November has earned its reputation because the same broad physical setup has produced severe storms over and over again. The White Hurricane of November 1913 remains the largest inland maritime disaster in US history, in terms of ships lost, with about a dozen major shipwrecks and an estimated 250 lives lost, according to the National Weather Service. The Fitzgerald storm of November 1975 remains one of the most famous Great Lakes disasters, and the November 1998 storm was notable enough that forecasters explicitly compared it with 1975, while also noting that this later storm was forecast days in advance, and most marine traffic sought shelter before conditions became excessive. That is an important detail. The weather pattern remained dangerous. Human response improved. The memory did part of the work. That point matters because the gales do not only mean loss, they also mean adaptation. One of the clearest lessons of the modern era is that better forecasting changes outcomes even when it does not change nature. NOAA's Great Lakes Operational Forecast System now produces 5-day, 120-hour forecasts of conditions such as water levels, currents, and temperatures, and NOAA's operational and experimental wave systems provide model guidance for wave heights across the basin. Marine forecasters combine those models with buoy data, coastal observations, radar, satellites, and their own judgment to issue open lake and nearshore forecasts, warnings, and hazard products. In earlier eras, mariners often had only local observation and broad synoptic guidance. Today they can access wave forecasts, radar imagery, wind guidance, and marine warnings with far greater precision. So the gales of November mean not only danger, but also the long effort to become less surprised by that danger. Even so, the gales still mean limits. Forecasting is not control. That distinction is one of the most important in the whole story. A modern captain can know far more about the expected wind field, wave heights, and storm track than a captain could know a century ago, yet still face a situation in which the only wise decision is delay, diversion, or shelter. Better data widen the window for good judgment, but they do not erase the need for it. The November 1998 storm is a good illustration of that. The National Weather Service noted that it was forecast days in advance, and that most traffic sought safe harbour before the strongest winds arrived. That is a success story, but it is a success story built on restraint. The lake did not become gentler. People simply had more warning and acted on it. So the gales mean that the smartest maritime decisions are often the least dramatic ones. Sometimes the best seamanship is refusing to become a story. They also mean cold, and cold changes everything. The National Weather Service warns that sudden cold water immersion can cause cold shock, including involuntary gasping and rapid breathing, and that this can be dangerous even in water warmer than many people expect. That fact turns November into something much more severe than a month of rough surfaces and grey skies. It means that if something goes wrong, the consequences accelerate. A person overboard may not have the time their instincts imagine they have. Dexterity can fall away. Breathing can become uncontrolled. Self-rescue becomes harder. Rescue itself takes time on water this large. So the gales of November mean that the penalty for even a small mistake rises sharply. a slipped footing, a failed line, a bad approach, a bit of ice on deck, a badly timed wave over the rail. Any one of these can become much more serious because the water is no longer merely wet. It is physiologically hostile, and because the water is so large, the gales mean distance as well. Distance to shelter, distance to the lee shore, distance to search and rescue, distance to a decision that should have been made an hour earlier. This is part of why Great Lake storms have such a particular psychological weight. They do not merely happen near a person. They happen across a field of exposure that can take time to cross even in good conditions. A harbour on a chart may look close enough to inspire confidence, but in rising seas, poor visibility, and falling temperatures, close enough can turn into not fast enough. That is why the navigation system with its harbours, channels and locks matters so much, and why mariners read forecasts as route information rather than background scenery. The gales mean that geography itself becomes part of the calculation. On the lakes, weather is never only weather. It is weather plus distance plus what lies between you and safety. There is another meaning too, and it has to do with work. The gales of November are famous partly because they interrupt labour, not just leisure. The Great Lakes are a working waterway. Ships carry raw materials, manufactured goods, and bulk cargo through a system essential to the regional economy. That is why storms here have always mattered in a very grounded way. They affect freight, timing, industry, ports, and livelihoods. A November gale is not just an impressive natural display. It is also a challenge to schedules, commerce, and the people whose jobs require them to weigh risk against necessity. That practical dimension gives the month a different character from storm seasons in places where the main story is recreation. On the Great Lakes, November weather has always spoken directly to working lives. That is one reason the memory of the month stays so firm. It has been attached to paychecks, cargoes, communities and industries for generations. At the same time, the gales mean preservation of consequence. On the Great Lakes, wrecks are often preserved exceptionally well by cold fresh water, and that has made the bottom of the basin into a kind of record of what these storms and hazards have done over time. The lakes are famous not only for their wreck count, but for the startling condition of many wrecks that remain. That gives the region a long memory below the surface as well as above it. The gales of November therefore mean that mistakes, miscalculations, structural failures, and impossible moments are not erased quickly. They are stored. They are mapped, studied, photographed and remembered in museums, sanctuaries and maritime reports. The lakes do not simply take, they keep evidence. That too adds weight to the phrase. It is not folklore resting on imagination. It is folklore resting on underwater proof, and perhaps that is the heart of it. The gales of November really mean that the Great Lakes are a place where usefulness and danger live side by side without contradiction. The same waters that supply drinking water to millions, support transportation, shape regional weather, and anchor communities are also perfectly capable of becoming violent, cold, and lethal when the season arranges the elements in a certain way. We often prefer our landscapes to have one personality at a time, friendly or hostile, useful or dangerous, beautiful or severe. The Great Lakes refuse that simplicity. November makes the refusal obvious. It is the month when the lakes remind everyone within reach that scenic value and destructive power are not opposites. They are often neighbours. So in the end, the gales of November mean humility more than drama. They mean that there are places in the modern world still large enough, physical enough, and seasonally powerful enough to make technology work hard for partial certainty rather than total control. We can model the lakes now, we can forecast them better. We can issue warnings earlier, route traffic more intelligently and prepare more effectively than earlier generations could. That is real progress, and it matters. But the continued need for all that effort tells its own story. We built better systems not because the lakes became safe, but because we finally got better at admitting how unsafe they can be. Forecast models, wave guidance and hazard warnings are not signs that nature has been tamed. They are signs that people have learned to take it more seriously. And there is one final meaning that belongs more to the quiet end of the evening than to the operations room or the wheelhouse. The gales of November mean that time matters. Not in the abstract, not in a philosophical classroom sense, but in the ordinary human way. A season turns. A lake keeps its heat a little longer than the land. A storm arrives a little stronger than expected. A decision is made an hour sooner or later. A forecast is heeded or ignored. A harbour is reached or missed. So much of this story comes down to timing. That is what makes the phrase feel heavy. It carries weather, history, work, caution, and loss. But underneath all of them is timing. November is when the Great Lakes and the atmosphere fall out of step with each other in exactly the way that makes storms most effective. Once you understand that, the phrase stops sounding romantic and starts sounding precise. It is really just a regional way of saying that nature has a season for reducing error margins. So wherever this finds you tonight, far from any shoreline or perhaps near one you know well, this is what the gales of November really amount to. They are not a legend pasted onto the Great Lakes from the outside. They are the lakes speaking in their clearest late autumn language. They say that size matters, timing matters, preparation matters, and cold water does not negotiate. They say that even inland water can become oceanic in consequence. They say that memory belongs not only in songs and museums, but in forecasts, route choices, life jackets, harbour plans, and the quiet judgment that decides whether today is a crossing day or a waiting day. And if there is something oddly calming in that clarity, perhaps it is because clear limits, once understood, are easier to respect than vague fears. The lakes do not ask for awe, they ask for seriousness. November simply makes the request harder to ignore. If you found some calm in this long drift through cold water, storms, freighters, forecasts, and the difficult reputation of late autumn on the inland seas, I would be grateful for the company. And if this quiet corner of science and story helped you settle a little, then that is a good place to leave it. The lakes will go on doing what they have always done, and the weather will go on crossing them in its own season and on its own terms. But for now, the charts can be folded, the radio can fall quiet, and the shore, wherever yours may be, can remain still.